Hello there and welcome to Physics with William, where curiosity can slow down for a while and difficult ideas are allowed to arrive one step at a time. Tonight we're going to look at something that seems simple at first and then becomes less certain the longer we examine it. We're going to ask whether particles are really the basic pieces of the universe. Most of us are introduced to matter through pictures of tiny objects. An atom is shown as a small centre surrounded by smaller particles. Protons, neutrons and electrons are presented as the parts inside ordinary matter. Later we learn that protons and neutrons contain quarks. Photons carry light. Neutrinos pass through planets with very little interaction. The list grows, but the basic picture often stays the same. Reality appears to be built from extremely small things, rather like a complicated machine made from pieces too tiny to see. That picture is useful. It helps us organise what we observe, and it gives us a practical way to talk about experiments. A particle can enter a detector, transfer energy, change direction, or leave a track. Scientists can measure those events with remarkable precision. Yet the word particle can quietly suggest more than the evidence actually tells us. It can make us imagine a miniature bead, a hard speck, or a little object with a clear boundary. Modern physics does not give us such a comfortable image. An electron is not simply a smaller version of a grain of sand. A photon is not a tiny glowing ball moving through space. When physicists describe these things carefully, they use ideas that are less familiar than ordinary objects. They speak about quantum fields, probabilities, interactions, and excitations. In that description, what we call a particle may be more like a temporary pattern than a permanent piece of material. Before we go further, where are you listening from tonight? Are you in a quiet room, on a late train, or lying in bed while the rest of the house has finally settled down? It is an appropriate question for this subject, because wherever you are, the space around you is not empty in the simple sense. According to our best current theories, fields extend through that space. They are present in the room, inside the walls, in the air, and throughout your body. Even a place that looks completely still is not necessarily inactive at the deepest level. If you find this kind of slow scientific discussion useful, you can like the video and subscribe to the channel. It helps other people find this quiet corner of physics, including those who enjoy learning, and those who intend to learn but may be asleep before the most difficult part arrives. Either outcome is acceptable. Now imagine a large, calm body of water. For the moment, do not think about individual drops. Think about the surface as a whole. A wave can move across it. The wave has a location, a speed, and an amount of energy. It can meet another wave, interfere with it, change shape, or fade away. We can point to the wave and discuss what it does. We can even treat it as a separate thing for many practical purposes. Still, the wave is not made from a special substance added to the water. It is a pattern in the water. This comparison is not perfect, and we should not push it too far. Quantum fields are not ordinary fluids, and particles are not exactly water waves. The comparison is useful because it changes the question. Instead of asking what a particle is made from, we can ask what underlying system is disturbed when a particle appears. Quantum field theory gives a serious and highly successful version of this idea. In this framework, fields are not optional background scenery. They are central. There is an electron field, and what we identify as an electron is an excitation of that field. There is an electromagnetic field, and what we identify as a photon is an excitation of that field. Other known particles are described in related ways. A particle is not placed into a field as a pebble might be dropped into a pond. The particle is a particular state of the field itself. This helps explain one of the strangest facts in nature. Every electron appears to be exactly like every other electron. They have the same electric charge, the same mass, and the same basic behaviour. There are no heavy electrons, slightly faded electrons, or electrons with personal preferences. An electron in your hand is indistinguishable from an electron produced in a laboratory on the other side of the planet. As far as physics can determine, there is no hidden serial number. If electrons were tiny manufactured objects, this perfect sameness might seem surprising. Even the best factory produces small differences. One screw may be fractionally heavier than another. One glass bead may contain a microscopic flaw. Natural objects vary even more. Stones, clouds, trees, and planets all carry the marks of their individual histories. Excitations of a single field do not have that problem. The same field exists everywhere, and each electron is a standard excitation of it. The field determines the properties. This is similar to the way a musical instrument can produce repeated notes with the same basic character. Each note happens at a different time, but the instrument and the mode of vibration define what the note is. The comparison again has limits, but it gives us a reason identical particles can be truly identical. They may not be separate objects manufactured one by one. They may be repeated expressions of the same underlying system. This shift also changes how we think about creation and destruction. In everyday life, objects do not usually appear from nowhere. A cup can break, but its material remains in the pieces. A chair can burn, but matter and energy continue in other forms. Particles behave differently in experiments because particle number is not always fixed. Under the right conditions, energy can produce particles. Particles can also disappear through interactions, with their energy and other conserved properties transferred elsewhere. The language of appearance and disappearance can sound dramatic, but quantum field theory handles it naturally. If a particle is an excitation, then creating a particle means placing the field into a more excited state. Destroying a particle means changing the field into a state with one less excitation, while the interaction produces other effects. Nothing needs to pop into existence without rules. The deeper system changes its condition. A familiar example involves light. An atom can release energy and produce a photon. Later, another atom or detector can absorb that photon. In a simple particle picture, it may seem as though a tiny object was manufactured, sent across space, and then erased. In the field picture, the electromagnetic field was excited in a specific way. That excitation travelled and interacted, and the field ended in a different state. The photon is real because it carries measurable energy and produces measurable effects. It does not need to be a permanent lump of substance in order to be real. That distinction is important. Saying that particles may not be fundamental does not mean that particles are imaginary. It does not mean detectors are confused, or that matter is an illusion. A wave in the ocean is real enough to move a boat. A sound wave is real enough to wake a sleeping person, usually at the least convenient hour. A storm is real enough to change a landscape, even though a storm is a pattern involving air, water, temperature, and pressure, rather than a single solid object. Emergent things can be completely real at the level where they operate. Temperature is a useful example. A single molecule does not have a temperature in the ordinary sense. Temperature describes the collective motion of many particles. Once enough particles are present, temperature becomes measurable, predictable, and important. It can cook food, melt ice, and make a bedroom uncomfortable. Its emergent nature does not reduce its reality. The possibility we are exploring is that particles may be similar. They may be stable and measurable patterns that arise from something deeper. Quantum field theory already takes a major step in that direction by treating particles as field excitations. The next question is whether the fields themselves are fundamental. Physics has reached this kind of boundary before. Atoms were once considered indivisible. The word itself came from the idea of something that could not be cut. Experiments later showed internal structure. Atomic nuclei contained protons and neutrons. Those particles turned out to contain quarks. Each discovery did not make the earlier level useless. Chemistry still works with atoms. Nuclear physics still works with protons and neutrons. The deeper explanation changed what counted as basic. It is tempting to assume that this process must continue forever. Perhaps every layer contains another smaller layer. That is possible, but it is not the only option. The deeper level may not consist of smaller objects at all. It could involve extended structures, information, relations, symmetries, or a network that does not resemble space as we normally experience it. String theory offers one well-known example. In its basic picture, what we call different particles may come from different vibrational states of a more fundamental object. An electron and another particle would not need to be made from different substances. They could be different modes of the same underlying kind of structure, rather as one string can produce different notes. This idea is attractive because nature contains many particle types, and a theory that describes them as different states of one deeper system may provide a more unified explanation. Still, string theory has not been experimentally confirmed as the final description of nature. It remains a broad research program with impressive mathematical structure and unresolved physical questions. It is one possibility, not a settled answer. Other approaches begin from different starting points. Some physicists study whether space and fields might emerge from quantum information. In that view, relationships between quantum systems may be more basic than objects located in a pre-existing space. Entanglement, which links the possible outcomes of quantum systems in ways that ordinary probability cannot reproduce, may help organize the structure we later interpret as geometry or matter. This can be difficult to picture, because human intuition expects objects first and relationships second. We imagine two things existing and then forming a connection. A more radical theory might reverse that order. The relationships could be primary, while the things we call particles appear as stable features within the network of relationships. A simple social comparison may help, although it should not be taken literally. A queue exists because people stand in a certain order. The queue is not an extra object placed beside them, yet it has structure. It can grow, shrink, move, and split. Its properties depend on relationships among the people. If everyone leaves, the queue disappears. In a deeper physical theory, particles might be persistent structures defined by relationships, though the actual mathematics would be far more demanding than waiting politely for coffee. Symmetry provides another route. In physics, symmetry is not just visual balance. It describes transformations that leave important features of a system unchanged. Symmetries help determine which particles can exist, how they behave, and which interactions are allowed. Some properties we assign to particles may reflect the structure of these symmetries rather than material ingredients hidden inside them. This is already familiar in modern particle physics. Particles are classified by quantities connected to symmetries, and the forces between them are described through mathematical structures that impose strict rules. From this point of view, a particle can look less like a tiny object and more like a permitted way for the underlying laws to express themselves. The phrase permitted way may sound as though nature is following instructions written somewhere outside the universe. That is not what physicists mean. The laws are descriptions of patterns that remain consistent across observations. We do not know why the universe has exactly these patterns rather than others. We only know that symmetry has become one of the most powerful guides in discovering what can happen. There is also the possibility that different particles are different phases or states of one deeper quantum system. Matter already gives us examples of one substance behaving in very different ways. Water can be solid, liquid, or gas. The molecules remain the same, but the collective state changes. In more complex materials, collective behavior can produce entities that act like particles, even though they are made from the coordinated motion of many underlying components. Physicists call some of these entities quasi-particles. They occur in solids and other many body systems. A quasi-particle can carry energy and momentum, interact and behave as though it were a particle, even though it is really a collective disturbance in the material. The existence of quasi-particles shows that particle-like behavior can emerge from a deeper system. It does not prove that electrons or photons are quasi-particles of an unknown cosmic material, but it gives us a working example of how apparent particles can arise without being fundamental objects. One such example is a hole in a semiconductor. When an electron is missing from a place where it could normally be, the absence can move through the material and behave as though it were a positively charged particle. Nothing small and positive has been inserted into the gap. The coordinated behaviour of many electrons makes the missing electron act like a mobile entity. Engineers can calculate with it and build technology around it. An absence becomes useful enough to carry current through a device, which is a fairly impressive career for something that is not there in the usual sense. Collective systems can produce other particle-like excitations as well. Some behave in ways that no fundamental particle in empty space is known to behave. Their properties depend on the environment from which they emerge. This teaches a cautious lesson. Observing particle behaviour does not by itself tell us that we have reached the deepest layer. The particles in the standard model may still be fundamental within the range of all current experiments. No confirmed experiment has revealed smaller components inside electrons or quarks. When physicists call them elementary particles, they mean that no internal structure has been detected. That is an experimental statement, not a guarantee that no deeper description exists. The difference matters because science works with what can be tested. A theory may be elegant, unified, and pleasing to the mind, but it must eventually connect with observations. The idea that particles emerge from something deeper becomes physics only when it produces clear predictions or explains known facts better than competing theories. Until then, it remains a serious possibility rather than a conclusion. There are practical reasons this question is hard. The deeper structure, if it exists, may reveal itself only at energies far beyond what present machines can reach. It may affect nature through tiny deviations that are difficult to separate from experimental noise. It may also require a new way of thinking before the right test can even be designed. Past discoveries often depended on both better instruments and better concepts. Scientists did not see atoms directly in the earliest atomic theories. They inferred them from regularities in chemistry and the behaviour of gases. The internal structure of atoms became clear through experiments that produced results the older picture could not explain. Quarks were not first introduced because someone found a tiny photograph of one. They were proposed because patterns in particle behaviour suggested an underlying organisation. A deeper theory of particles may arrive in a similar way. Researchers might notice that the masses and interactions of known particles follow a pattern that current theory treats as accidental. A new framework could explain why those values and relationships occur. Evidence could appear through cosmology, black holes, quantum gravity, or unexpected behaviour in precision measurements. There is no promise that nature will make the answer convenient. For now, the field description already gives us a useful change in perspective. The room around you is not best understood as empty space containing isolated little objects. Fields are present throughout it. What appears as matter consists of stable excitations and bound states of those fields. The solidity of a table does not come from tiny hard balls packed without gaps. It comes from quantum fields, electromagnetic interactions, and rules that prevent certain particles from occupying the same states. Your own body is stable not because its particles are miniature bricks, but because the relevant fields interact in consistent ways. Electrons maintain the structure of atoms. Atomic nuclei remain bound through the strong interaction. Molecules form because quantum states allow certain arrangements and resist others. At the level of daily experience, this produces skin, bone, fabric, wood, glass, and the mattress currently doing most of the practical work in this listening experience. Nothing about this makes ordinary reality less dependable. The emergent level is the level we live in. You do not need quantum field theory to make tea, although it is quietly involved in the kettle, the electricity, the chemistry of the water, and the fact that the mug does not fall through your hand. Different descriptions are useful at different scales. A weather forecast does not track every air molecule. Biology does not begin every explanation with quarks. Chemistry does not need to discuss quantum gravity whenever two substances react. Each science works with stable patterns that emerge from deeper levels. The patterns can have their own rules, concepts, and causes. Particles may occupy a similar position. They may be the correct language for a certain level of nature without being the final language. The electron can remain a precise and essential physical entity, even if a future theory explains it as a state of something more basic. A melody remains recognizable even after we learn about vibrations, pressure changes, and the nervous system. Understanding the deeper process does not erase the melody. It explains how the melody is possible. That is the central idea we will keep in view. Particles are not being dismissed. Their effects are measurable, and the theories that describe them are among the most accurate scientific theories ever developed. The question is whether the category of particle belongs to the foundation of reality, or whether it appears when a deeper structure behaves in a particular way. To approach that carefully, we first need to understand what physicists mean when they say a particle is an excitation of a field. The phrase can sound like a replacement of one mystery with another. It becomes clearer when we examine how fields are used, why they fill all of space, and how a single field can produce events that detectors record as separate particles. That is where the next part of the discussion begins, with the electron field already present everywhere, and an electron appearing not as a tiny object added to the universe, but as one specific way that field can be active. To understand how a particle can really be a field, it helps to begin with something more familiar. A field in physics is a quantity that has a value at every location in space. The temperature in a room can be described as a field because one side of the room may be slightly warmer than the other. Wind can also be described using a field because the air has a speed and direction at every point. A weather map does not need to place a separate object at each location. It describes a condition spread across an entire region. The same general idea appears in electromagnetism. An electric field can fill the space around a charged object. A magnetic field extends around a magnet. These fields can affect other objects even when nothing visible connects them. If you have ever watched two magnets push apart without touching, you have seen the effects of a field. The empty-looking space between the magnets is not doing nothing. It has physical properties that determine how the magnets interact. Classical fields were already important before quantum mechanics was developed. Physicists used them to describe electricity, magnetism, light, gravity, fluids, and many other systems. A classical field can carry energy and produce waves. If the field is disturbed in one place, that disturbance can travel through space. Light is a good example. In classical physics, light is a wave in the electromagnetic field. The electric and magnetic parts of the field change together as the wave moves. This description explains reflection, refraction, interference, and the colours produced when light passes through a prism. It works so well that engineers still use it to design lenses, antennas, communication systems, and many other technologies. The difficulty appeared when scientists examined how light interacts with matter at very small scales. Light sometimes behaved as a smooth wave, but in other experiments it transferred energy in separate amounts. A detector did not always receive a continuous spread of energy. It registered individual events. This is where the photon entered the description. A photon is a single quantum of the electromagnetic field. The word quantum refers to a discrete amount. Instead of the field exchanging any arbitrary amount of energy, certain interactions occur in distinct steps. A photon is one such step. It can be tempting to picture the photon as a tiny pellet carried by the wave. That image causes problems. The photon is not a small bead hidden inside the electromagnetic field. It is a particular excitation of the field. The field itself is the underlying entity, and the photon is one way that field can carry energy and momentum. Think about a long rope stretched across a room. If one end is moved, a pulse travels along the rope. The pulse has location and carries energy. It can reach the other end and move whatever is attached there. Still, the pulse is not an additional piece of rope. It is the rope behaving in a particular way. A photon is not literally a pulse in a material rope. but the comparison points in the right direction. The electromagnetic field can be in a low energy state, or it can be excited. A photon is a quantized excitation of that field. The same reasoning applies to matter. An electron is an excitation of the electron field. According to quantum field theory, the electron field exists throughout space. It is present whether or not an electron is currently detected in a particular location. When the field has the right kind of excitation, we describe that excitation as an electron. This may seem like a strange way to talk. We are used to thinking that a field must belong to an object. A magnetic field belongs to a magnet. A temperature field belongs to a room full of air. The electron field, however, is not produced by a collection of tiny electrons. It is the other way around. Electrons are produced as excitations of the field. The field comes first in the theory. The particles are the states it can take. There is not only one field. Modern particle physics describes several quantum fields. There are fields associated with electrons, quarks, neutrinos, photons, gluons, and other known particles. These fields occupy the same space at the same time. They do not need separate containers. They overlap without being mixed together in the ordinary sense. The room around you contains the electromagnetic field, the electron field, quark fields, neutrino fields, and the Higgs field, among others. Most of these fields are not strongly excited in the air around you, but they are still part of the physical description. This sounds crowded, although nothing needs to feel crowded. Fields are not packed into space like layers of fabric in an overfilled suitcase. They are different physical quantities defined throughout space. Several fields can have values at the same location, just as a location can have a temperature, air pressure, sound level, and amount of light at the same time. When fields interact, particles can appear to transform into other particles. An electron can emit a photon. A photon with enough energy can contribute to the creation of an electron and its antimatter partner. Quarks can exchange gluons. Unstable particles can decay into lighter particles. In a theory built from permanent little objects, these events can look like complicated acts of construction and destruction. In quantum field theory, they are changes in the excitation patterns of interacting fields. Energy and other conserved properties move from one field to another. Some excitations disappear, while others are produced. Suppose an electron releases a photon. The electron does not open a tiny door and throw out a smaller object it was carrying. The electron field and electromagnetic field interact. The state of the electron field changes, and the electromagnetic field gains an excitation. That excitation is the photon. A detector later absorbs the photon. The photon does not simply vanish without consequence. Its energy and momentum are transferred through an interaction. The electromagnetic field loses that excitation, while the detector changes state. Perhaps an electron in the detector moves to a higher energy level. Perhaps an electrical signal is produced. The exact result depends on the detector. This is why particle creation and destruction are normal parts of quantum field theory. The theory does not require the number of particles to remain fixed. What must remain consistent are the relevant conservation laws. Energy does not disappear. Electric charge does not quietly wander away because it has somewhere else to be. The total physical accounting still works, even when the list of particles changes. Fields also help explain why experiments can reveal both wave-like and particle-like behavior. A quantum field can spread and interfere like a wave, yet when it interacts with a detector, the exchange occurs in discrete events. The same underlying description produces both kinds of observation. Consider the well-known experiment in which light passes through two narrow openings. When many photons are sent through, an interference pattern gradually forms on a screen. The pattern is associated with wave behavior. However, the screen records separate points, one detection at a time. Each photon produces a localized event. Sending photons individually does not remove the pattern. After enough detections, the same interference structure appears. Each event is local. but the probabilities that govern where events occur show wave-like interference. This result becomes less contradictory when the photon is understood as a quantum excitation rather than a miniature ball. The quantum field determines a range of possible detection outcomes. The excitation can be described in a way that extends across space. When an interaction occurs, the detector records a specific result. The phrase particle location must therefore be used carefully. In ordinary speech, an object either is or is not in a particular place. A cup can be on the table or in the cupboard. Quantum particles are not always described by definite positions before measurement. The theory gives probabilities for where an interaction may occur. This does not mean that nothing exists until someone looks at it. It means that quantum states do not always assign the same definite properties that classical objects have. Measurement is a physical interaction, not merely a person opening their eyes with sufficient enthusiasm. When a detector records an electron, the result is usually localized. A small region of the detector changes. That local mark encourages us to imagine that a tiny solid electron must have followed a narrow hidden path to that exact location. Quantum field theory does not always support such a simple story. The state can be spread out, while the interaction produces a local event. The same distinction appears in sound. A sound wave can fill a room, but a microphone converts it into events within a small device. That does not prove the sound existed only inside the microphone. Again, quantum fields are not ordinary sound waves, but the comparison helps separate the spread of a state from the location of a detection. There is another important difference between classical and quantum fields. A classical field can often be assigned a definite value at every point. A quantum field is described through a quantum state, which includes uncertainty. The field does not simply behave like a perfectly smooth substance with tiny waves moving across it. Even the lowest energy state of a quantum field is not equivalent to complete stillness. This lowest energy condition is called the vacuum state. In everyday language, a vacuum means empty space. In quantum field theory, the vacuum is the state in which there are no ordinary particles present, but the fields themselves still exist. The vacuum is not a hidden cloud of little particles constantly appearing as fully formed objects without rules. Popular descriptions sometimes create that impression. The actual theory is more careful. Quantum fields in the vacuum have measurable structure and fluctuations, but these should not always be pictured as ordinary particles briefly borrowing energy and then returning it. That image can be useful in limited calculations, yet it can also become misleading when treated as a literal film of events. What matters here is that removing all particles does not remove the fields. The vacuum is a state of the fields, not the absence of physical reality. This leads to an interesting reversal. Instead of beginning with particles and asking what fills the space between them, quantum field theory begins with fields that exist throughout space and asks which excitations are present. Empty space and matter are not made from entirely different categories. They are different states of the same collection of fields. An area with no electrons is not an area without the electron field. It is an area where the field has no electron excitation in the relevant state. An area through which a photon travels is a region where the electromagnetic field is excited in a particular way. The Higgs field provides another important example. It has a non-zero value even in the vacuum. Certain particles interact with this field, and that interaction is connected to their mass. This is not quite the popular image of particles pushing through a thick substance. The Higgs field does not slow particles through friction. Its role comes from the structure of the underlying quantum theory. The discovery of the Higgs boson provided evidence for an excitation of the Higgs field. The field itself was already part of the theory. The detected boson was a temporary excitation produced in high-energy collisions. It decayed almost immediately into other particles, which were then measured. The Higgs boson did not need to survive for long in order to be real. Stability is not a requirement for reality. Some particle excitations last for extremely long periods. Others exist for only a tiny fraction of a second. Their lifetimes depend on which transformations are allowed and how strongly they interact. An electron appears to be stable. A free electron does not simply decay into lighter particles because there is no allowed process that preserves all the required properties while producing a lower energy result. Other excitations are unstable and change rapidly. This resembles vibrations in an instrument. Some modes can continue for a relatively long time, while others lose their energy quickly. The duration depends on how the mode interacts with the rest of the instrument and its environment. The comparison does not capture every feature of particle physics, but it shows why a pattern does not have to be permanent. Fields also make the unity of nature easier to see. The electron in an atom and an electron moving through a wire are not two different kinds of object. They are excitations of the same electron field in different physical situations. The field does not belong to a specific atom or laboratory. It extends through the universe. An electron produced in a radioactive decay is not made from different electron material than one that has been part of an atom for billions of years. Their origin does not give them individual properties. Once the excitation exists, it is an electron. This is very different from ordinary manufactured objects. Two chairs may be built according to the same design, but they remain distinguishable. One may have a scratch. The other may have a loose leg that everyone politely ignores until a guest discovers it. Their histories remain attached to them. Electrons do not work that way. Swapping two electrons does not produce a physically new arrangement that allows us to say which one is which. Quantum theory treats their indistinguishability as a fundamental part of their behavior. The field picture makes this less surprising. We're not dealing with separate miniature objects that happen to look alike. We're dealing with multiple excitations of the same field. Asking which electron is the original one can become as meaningless as asking which part of a wave was the wave from 5 seconds ago. This does not mean electrons lack measurable properties. Each electron carries electric charge, energy, momentum, and a quantum property called spin. The point is that these properties describe the type of excitation and its state. They do not provide a hidden personal identity. Fields also interact locally. This means an interaction occurs at a particular region of space rather than through an unexplained immediate influence between arbitrarily distant locations. Quantum entanglement introduces correlations over large distances, but it does not allow ordinary information to be sent instantly. The underlying theory remains carefully structured around local interactions, even though the resulting quantum states can have relationships that challenge classical intuition. The success of quantum field theory is not based only on attractive ideas. It has produced exceptionally accurate predictions. Calculations involving the electromagnetic interaction match experimental measurements to an extraordinary degree. Particle accelerators test the predicted behavior of fields at high energies. Modern electronics, lasers, medical imaging, and much of contemporary technology depend on principles connected to quantum theory. Still, quantum field theory is not necessarily the final layer. It describes fields as fundamental ingredients, but it also relies on space and time. A field is defined across space and changes through time. General relativity tells us that space and time are themselves dynamic. They bend and respond to energy and matter. Combining quantum field theory with gravity remains one of the major unresolved problems in physics. At ordinary energies, physicists can treat quantum fields on a background of space and time with excellent results. In extreme conditions, such as the early universe or the interior regions associated with black holes, that separation becomes unreliable. If space, time, and fields all have to be described quantum mechanically, the familiar picture may change again. Fields might emerge from something deeper. The stage and the actors may both come from a structure that does not look like either one. There are hints that this could be possible. In certain areas of physics, very different field descriptions can represent the same underlying system. A theory involving particles and fields in one setting may be mathematically equivalent to a theory without the same apparent ingredients in another. These connections suggest that what looks fundamental in one description may be emergent in another. Condensed matter physics gives more concrete examples. In materials containing huge numbers of interacting particles, collective behavior can be described using effective fields. The excitations of those fields act like particles. They may carry energy, momentum, and other properties. Some behave as though they have masses or charges that are not properties of any single underlying component. The effective particle is real within the material, but it exists because of the organized behavior of the deeper system. Remove the material, and the excitation cannot continue in the same form. This raises a reasonable question. Could the particles we call elementary also be excitations of an underlying structure that we have not yet identified? The standard model treats them as excitations of quantum fields. A deeper theory might explain the fields as collective outcomes of more basic relations, strings, information, or another structure not yet understood. There is no confirmed answer. It would be misleading to say that physicists have discovered what lies below quantum fields. They have developed several possible frameworks, but none has received the level of experimental support enjoyed by quantum field theory and general relativity. Even without that deeper answer, the change from particle objects to field excitations is already significant. It tells us that the universe is not best imagined as an enormous box containing countless tiny beads. What we call objects arise from states of systems that extend through space. A table appears solid because quantum fields interact. Light reflects from it because the electromagnetic field interacts with charged excitations in the material. Your hand does not pass through the surface because the possible quantum states of the electrons in your hand and the table are constrained, and electromagnetic forces resist the overlap. At no point do we need tiny hard surfaces touching one another in the classical sense. The resistance is produced by fields and quantum rules. Solidity is an emergent result of interaction. This does not make the table less solid for practical purposes. It would still be unwise to test the field description by walking into it. Physics often allows several descriptions to be true at different scales. The table is a solid object in daily life, a molecular structure in chemistry, a system of atoms in atomic physics, and an arrangement of interacting quantum fields at a deeper level. The word particle remains useful because many field excitations behave as distinct units in experiments. They arrive at detectors in countable events. They carry definite packages of charge and other properties. They scatter in predictable ways. Under appropriate conditions, their motion can be approximated by paths. The mistake is not using the word particle. The mistake is assuming the word tells us that the entity must be a tiny solid object. An electron can be particle-like without being a bead. A photon can arrive as a discrete detection without being a pellet of light. Their particle behavior is one aspect of quantum fields, seen through the way those fields exchange energy and other quantities. Once this is understood, several strange facts begin to fit together. Particles can appear and disappear because excitations can be created and removed. Wave and particle behavior can coexist because a quantum field can spread while interactions occur in discrete events. Empty space can have physical properties because the fields remain present in their vacuum state. The field picture also prepares us for an even less familiar fact. Every excitation of a given field is perfectly identical to every other excitation of the same type. There is no way to mark one electron, follow its private identity, and distinguish it from another electron after the two have exchanged places. This is not merely a limitation of our instruments. It is built into the quantum description, and it changes the behavior of matter at every scale. Imagine placing two identical coins on a table. They may have the same design, the same year, and nearly the same weight, but they are still two separate objects. You can scratch one of them, leave the other untouched, and follow each coin as it moves. Even when they look alike, they have individual histories. One was in your left hand, the other was in your right. If you exchange their positions, something has changed. even if the arrangement looks the same. This ordinary idea of identity is so familiar that we rarely question it. Every object seems to be its own thing. 2 cups may come from the same factory, but one is the cup beside the kettle, and the other is the cup that has disappeared into somebody else's office. 2 grains of sand may look identical from a distance, yet under a microscope they have different shapes and different marks. Even the most carefully manufactured objects contain small differences. Particles do not behave this way. Every electron has exactly the same basic properties as every other electron. Every electron has the same mass, the same electric charge, and the same spin. No experiment has ever found an electron that is slightly heavier because it had a difficult morning, or one that carries a little more charge because it has been travelling for a long time. An electron created a moment ago is identical to an electron that has existed since the early history of the universe. The word identical may still sound too weak. Identical twins are extremely similar, but they are separate people. 2 digital files can contain the same information, but they may be stored in different locations. 2 factory-made screws can match closely, but they remain individual objects. Quantum particles of the same type are not merely similar copies, they are indistinguishable in a deeper sense. Suppose 2 electrons move toward each other, interact, and then move apart. In an ordinary collision between 2 balls, you could imagine painting one red and one blue. After the collision, you could follow the colours and determine which ball went in which direction. Electrons cannot be marked in this way without changing the physical state. There is no hidden label beneath their visible properties. Once the interaction is complete, asking which outgoing electron was the first incoming electron may have no physical answer. This is not simply a problem with our equipment. It is not that electrons are too small for us to follow properly. The theory does not assign them private identities that remain hidden from our instruments. The question itself can become meaningless. The field description makes this easier to accept. If electrons were separate tiny objects made one by one, their perfect sameness would be surprising. Quantum field theory says that every electron is an excitation of the same electron field. The field is present throughout space. An electron appearing here and another electron appearing somewhere else are 2 excitations of one underlying field. Think about 2 notes played on the same piano key. One note may be played in the morning and another in the evening. The sound waves are separate events, but neither note has a private substance that makes it a different kind of note. The key and the instrument determine its character. The notes can have different loudness or duration, but the basic type of vibration is the same. Electrons are not sound waves, and the electron field is not a piano. The comparison is useful because it removes the need for a factory producing tiny matching objects. One field produces the same kind of excitation wherever that excitation occurs. A more direct comparison comes from waves in a continuous system. Imagine 2 ripples moving across the surface of water. When they meet, they overlap. Afterward, waves continue moving away from the meeting point. It may be impossible to say which outgoing ripple is the original first ripple. The water has simply evolved from one pattern into another. The labels we placed on the incoming shapes were useful to us, but the water did not preserve them. Quantum particles retain measurable properties such as energy and momentum, so the comparison is not exact. Still, it shows how a system can contain several excitations without giving each excitation a lasting personal identity. This has consequences that reach far beyond philosophical questions about naming electrons. Indistinguishability changes the statistical behavior of matter. It determines how particles can share states, how atoms are structured, why materials have the properties they do, and why ordinary objects do not collapse into a much simpler arrangement. Quantum particles are divided into 2 broad families. One family includes particles such as electrons and quarks. These particles are called fermions. The other family includes particles such as photons and gluons. These are called bosons. The names are less important than the different rules they follow. Fermions resist sharing the same quantum state. Bosons are able to occupy the same state in large numbers. This difference is not caused by the particles making decisions. It follows from the mathematical structure used to describe indistinguishable quantum particles. Consider electrons inside an atom. They're attracted to the positively charged nucleus. If electrons behaved like ordinary objects, we might expect all of them to settle into the lowest available energy state. That would be similar to everyone entering a quiet room and choosing the same comfortable chair, which would quickly make the chair less comfortable than advertised. Electrons cannot all occupy exactly the same state. The rule that prevents this is known as the Pauli exclusion principle. It states that two identical fermions cannot occupy the same complete quantum state at the same time. As a result, electrons in an atom must fill different available states. Some remain close to the nucleus in lower energy arrangements. Others occupy states with higher energies and different spatial patterns. This layered organization produces the structure of atoms. The arrangement of electrons is responsible for much of chemistry. It determines how atoms bond, which elements react strongly, which remain relatively inactive, and how molecules form. The periodic table is not merely a list of different nuclei. Its repeating patterns arise largely from the way indistinguishable electrons fill available quantum states. Without the exclusion principle, atoms would not have their familiar sizes and structures. Electrons could pile into the same lowest state. The rich organization that supports chemistry would disappear. Carbon would not form the same range of molecules. Solids would not have the same resistance to compression. Biology would not have the stable molecular framework it requires. The fact that your hand does not pass through a table is partly connected to this rule. Electric repulsion between electrons is important, but exclusion also matters. The electrons associated with your hand cannot simply enter quantum states that are already occupied by electrons in the table. The combined system resists being forced into an arrangement that the quantum rules do not allow. This resistance contributes to the stability and volume of matter. A chair supports you not because its atoms are made from little solid marbles touching one another, but because fields interact and identical fermions cannot all crowd into the same states. What feels like solidity is the large-scale result of quantum restrictions. The same rule helps support white dwarf stars. A white dwarf is the dense remnant left after certain stars exhaust their nuclear fuel. Gravity tries to compress the star. The electrons inside are forced into a smaller region, but the exclusion principle prevents them from all occupying the same low-energy states. They must fill a growing range of states, and this produces a pressure that resists further collapse. This pressure is not ordinary heat pressure. It remains even when the star is relatively cool. It comes from the quantum behavior of indistinguishable fermions. A rule that seems highly abstract when discussed in a laboratory becomes strong enough to resist the gravity of a star. In still more extreme objects, neutrons can provide a related form of support. Neutrons are also fermions. In a neutron star, enormous gravitational pressure compresses matter to densities far beyond those found in ordinary materials. The quantum behavior of indistinguishable particles becomes central to the structure of an object containing more mass than the Sun packed into a region comparable in size to a city. Bosons follow a different pattern. Many bosons can occupy the same quantum state. Photons do this in lasers. A laser produces light in which large numbers of photons share closely matched properties. Their coordinated behavior creates a narrow, intense beam that can remain focused over long distances. Ordinary light from a lamp contains photons with many different energies, directions, and phases. They are not organized into the same collective state. Laser light is more coordinated because bosons are allowed to gather in the same state. This ability can also appear in collections of atoms. Some atoms behave as composite bosons under suitable conditions. When a gas of these atoms is cooled to an extremely low temperature, many of them can enter the same quantum state. The result is called a Bose-Einstein condensate. In this condition, the collection begins to behave in a coordinated way that cannot be described as a group of independent little balls. A large number of atoms share a common quantum state. Effects normally associated with tiny systems become visible across a larger region. Superfluidity provides another example of collective quantum behavior. Under the right conditions, certain fluids can flow with almost no resistance. They can move through narrow openings and behave in ways that ordinary fluids do not. The effect arises because many particles participate in a shared quantum state. These phenomena reveal why indistinguishability is not a minor detail. If particles carried hidden labels, exchanging them would always create a new physical arrangement. Quantum statistics would be different. The collective behavior of matter would change. To see the problem, return to the coins. Place one coin on the left and one on the right. Call them coin 1 and coin 2. Swapping them changes which coin is in each location, even if the visible arrangement remains similar. There are two possible labelled arrangements. Now imagine that no label exists, even in principle. There is simply one coin on the left and one on the right. Exchanging them does not produce a new physical situation. Counting it as a separate arrangement would be counting the same state twice. Quantum theory must take this into account. When the possible arrangements of identical particles are combined, exchanging two particles can affect the overall quantum state in one of two main ways. For bosons, the state remains unchanged. For fermions, the exchange changes the mathematical sign of the state. That sign is not a visible mark attached to a particle. It affects how different possibilities combine. When two identical fermions are placed in the same state, the relevant contributions cancel. This is the basis of the exclusion principle. No equations are needed to understand the general result. Nature does not treat the two fermions as separately labelled objects. Their combined state must be constructed in a way that respects their indistinguishability. The structure of that combined state prevents complete overlap. For bosons, the possibilities reinforce rather than cancel. This makes it more likely for bosons to occupy states that already contain other bosons. In suitable systems, bosons tend to gather into shared states. This difference is connected to spin. Fermions have one category of spin, while bosons have another. Spin is a quantum property. That does not mean a particle is literally rotating like a small planet. The name came from an early attempt to build an intuitive picture, but the actual property is part of the way quantum states respond to rotations and transformations. A deep result in quantum field theory connects spin with statistics. Particles with one kind of spin must behave as fermions. Particles with the other kind must behave as bosons. This connection is not added as a convenient rule after experiments. It follows from the consistency of quantum field theory, together with basic requirements about how physical influences behave in space and time. The result again points away from the image of particles as independent little objects. Their behavior depends on the structure of the underlying fields and the symmetries those fields obey. The rule governing a collection of electrons is not explained by a mechanical feature inside each electron. It comes from the kind of quantum field an electron is an excitation of. Indistinguishability also makes it difficult to tell a continuous story about individual particles during interactions. In particle collision experiments, physicists prepare an initial state and measure a final state. They can calculate the probabilities of different outcomes with extraordinary accuracy. What they cannot always do is assign a unique classical route to each particle between those observations. Suppose two identical photons enter an experimental device from different directions, and two photons later emerge. There may be no meaningful fact about which outgoing photon corresponds to which incoming photon. The measurable result belongs to the complete quantum process. In some experiments, indistinguishable alternatives interfere with each other. If there are several ways for an outcome to occur and no physical measurement can distinguish those ways, quantum theory combines the possibilities. The final probability depends on their interference. This is not interference caused by two hidden objects bumping into each other. It is interference between possible descriptions of the same complete event. The inability to label identical particles becomes an observable effect. A well-known example involves two identical photons arriving at a beam splitter, which is a device that can transmit or reflect light. Under carefully controlled conditions, the two photons tend to leave together rather than separating along different paths. The result depends on their bosonic nature and their indistinguishability. If information exists that makes the photons distinguishable, perhaps a difference in arrival time or another measurable property, the effect weakens. When the distinguishing information is removed, the quantum interference returns. Identity is not merely unknown. The presence or absence of physical distinctions changes what the system does. Electrons show related interference effects with the opposite statistical behavior. Their fermionic nature prevents certain shared outcomes and alters the patterns found in scattering experiments, atoms, metals, and other systems. Inside a metal, many electrons move through a structure formed by atomic nuclei. They are not best described as tiny labelled balls weaving around one another. They occupy collective quantum states that extend through the material. The exclusion principle determines which states are filled and which remain available. Electrical conduction depends on this arrangement. Most electrons cannot simply change into any nearby state because many of those states are already occupied. Only electrons with access to available states can respond in the required way when an electric field is applied. The properties of metals, insulators, and semiconductors arise from the organization of these collective states. Modern electronics therefore depends not only on electrons having charge, but also on identical electrons lacking individual identity and obeying fermionic statistics. There is a subtle issue here. We often speak about the electron in a particular atom or the electron moving through a wire. This language can be useful, especially when interactions keep an excitation concentrated in a certain region. It does not mean the electron carries a permanent label. An electron can become bound to an atom, leave the atom, enter another system, and become indistinguishable from every other electron there. The idea of ownership is approximate. Atoms do not keep personal collections of electrons with carefully maintained records. In chemistry, it is common to describe electrons as being shared between atoms. This is not only a figure of speech. In a molecule, an electron state may extend across several nuclei. Insisting that the electron belongs to one specific atom may not match the best physical description. The absence of particle identity also affects how we think about continuity through time. A person remains identifiable because the body and memory change gradually. A familiar object can be followed because its material structure persists. A particle does not need this kind of personal continuity. When an electron is absorbed and another electron is emitted later, there may be no physical basis for claiming they are the same electron. The conserved properties continue through the interaction, but the identity of a specific particle does not have to continue. This can sound as though an electron is less real than an ordinary object. A better conclusion is that reality does not require every entity to possess the kind of identity familiar from daily life. Fields, states, and interactions can be real without behaving like labelled possessions. A flame is real, but the material in the flame constantly changes. A traffic jam is real, though the cars entering one end are not the same cars leaving the other. A whirlpool can remain in roughly the same place while different water passes through it. The stability belongs to the pattern rather than to a fixed collection of ingredients. Particles may be even more strongly tied to patterns. An electron is a stable type of excitation, not a permanent piece of electron material. The type persists because the field and its rules persist. Individual identity is unnecessary. This view also explains why nature can be described so economically. The universe does not require a separate instruction sheet for every electron. The electron field defines what all electrons are. Wherever the field is excited in the appropriate way, the same properties appear. The laws do not need to remember where an electron came from, how old it is, or which interactions it has experienced. Those details may affect the state of the system, such as its position or energy, but they do not alter the basic identity of the particle type. At this point, another question begins to form. If particles have no private identity, and if they are only excitations of fields, what exactly happens when a particle is created or destroyed? The phrase destroyed sounds as though a real object has been erased. The phrase created sounds as though a new object has been assembled from nothing. Neither picture describes the process very well. When fields interact, excitations can be transferred, combined, or converted. A particle count can change while the underlying physical system continues to follow strict conservation rules. The absence of individual identity is essential to this process. When an electron and its antimatter partner interact and produce photons, there is no need for the electron's personal substance to continue inside one particular photon. Energy, momentum, charge, and other relevant properties determine the allowed outcome. The original particle labels do not survive because those labels were never fundamental. A particle can therefore be stable and measurable without being a permanent unit of substance. It can enter an interaction as one excitation and leave no particle of the same type behind. Other excitations appear instead, carrying forward everything the laws require, while the question of where the original object went gives way to a more accurate question about how the fields changed. A particle can enter an interaction as one excitation and leave no particle of the same type behind. Other excitations appear instead, carrying forward everything the laws require. This is the point where everyday language begins to become unreliable, because words such as creation and destruction sound more absolute than the physical process really is. In ordinary life, creating something usually means assembling it from existing material. A carpenter creates a table from wood. A baker creates bread from flour, water, yeast, and salt. Destroying the table or the bread does not remove the material from the universe. It changes the arrangement. We are comfortable with this because the pieces remain available to be counted. Particle physics does not always offer the same visible continuity. An unstable particle can disappear, and two or more different particles can be detected afterward. A photon can be absorbed by matter and leave no photon behind. Under suitable conditions, energy concentrated in a collision can produce particles that were not present before the collision. The list of particles changes, even though the complete physical process remains controlled by strict rules. Quantum field theory describes this without requiring tiny objects to be assembled or erased. Each particle type is connected to a field. When fields interact, their patterns of excitation change. A field can gain an excitation, lose one, or transfer energy and other properties to another field. The number of particles is therefore not always fixed. Begin with a simple case involving light and an atom. An atom can start in an excited state, which means its electrons are arranged with more energy than the lowest available arrangement. The atom may later move to a lower energy state. The energy difference is carried away by an excitation of the electromagnetic field. We call that excitation a photon. Nothing inside the atom had been storing a tiny photon like a coin in a pocket. The photon did not exist as a separate object waiting to be released. The interaction changed the state of the atom and excited the electromagnetic field. A new photon was present after the transition because the field had entered a state containing one photon. The reverse process can also occur. A photon reaches an atom with the right energy and is absorbed. The atom moves to a higher energy state and the photon is no longer present. Its energy has not vanished. The electromagnetic field has lost one excitation, while the atomic system has gained energy. This process happens in ordinary materials all the time. Light striking a surface may be reflected, transmitted, or absorbed. When it is absorbed, photons do not collect inside the material as intact little objects. Their energy changes the states of electrons, atoms, or the material as a whole. It may eventually become heat, produce electrical current, or be released again as light with different properties. A solar panel provides a practical example. Photons from sunlight interact with electrons in the material. The energy allows some electrons to move into states where an electric current can be produced. The incoming photons are absorbed. Their energy becomes part of a different arrangement of excitations in the material and its electrical circuit. A camera sensor works through related processes. Light from a scene reaches the sensor, photons are absorbed, and electronic signals are produced. Each detection event records the transfer of energy from the electromagnetic field into the material. The image is built from many such interactions. The phrase photon disappearance may sound mysterious, but it is no more mysterious in the theory than a vibration stopping in one part of a system while causing motion somewhere else. The form changes. The total accounting remains consistent. Matter particles can also appear and disappear, although additional rules apply. Electric charge must be conserved. Energy and momentum must be conserved. Other quantum properties restrict which reactions can occur. A process is possible only when all relevant requirements can be satisfied. Consider an electron and a positron. A positron is the antimatter partner of the electron. It has the same mass as an electron and the opposite electric charge. When an electron and a positron meet under suitable conditions, they can annihilate and produce photons. The word annihilate encourages a dramatic picture of matter being converted into nothing. That is not what happens. The electron excitation and the positron excitation are removed, while the electromagnetic field gains excitations. Their mass, energy, motion, and other conserved properties are carried by the resulting photons. The total electric charge before the interaction is zero, because the negative charge of the electron and the positive charge of the positron cancel. The photons also carry no electric charge, so the accounting works. Energy and momentum determine the number and directions of the photons that can be produced. The process can run in the opposite direction. A sufficiently energetic photon interacting in the presence of another object or field can contribute to the production of an electron and a positron. This is called pair production. A single photon travelling through empty space cannot ordinarily produce the pair by itself, because energy and momentum could not both be conserved. Another participant is needed to take part in the exchange. This may be the electromagnetic field near an atomic nucleus, another photon, or some other system. When pair production occurs, the electron and positron are not carved out of hidden material stored inside the photon. The energy available in the interaction places the electron field into a state containing an electron and a positron. After the process, both particles can be detected. Mass is therefore not a permanent substance separate from energy. It is one property of a physical state. Concentrated energy can produce massive particle excitations when the conditions and conservation rules allow it. Massive particles can also disappear in reactions that transfer their energy into other excitations. This does not mean any collection of energy can become any particle at any time. Nature is highly selective. The energy must be sufficient. The interactions must exist. Charge and other properties must balance. Some processes are common, some are rare, and some are forbidden. An unstable particle gives a clear example of these restrictions. Suppose a heavy particle can interact in a way that produces several lighter particles. If the total rest mass of the final particles is lower, the remaining energy appears in their motion. The original excitation decays, and the fields associated with the final particles become excited. Physicists describe such events as decay. The word may suggest a physical object slowly falling apart, like fruit left too long on a kitchen counter. Many particle decays do not work that way. The original particle may not contain the final particles as smaller pieces. Instead, the interaction allows one field excitation to be replaced by a different collection of excitations. A muon illustrates this point. A muon resembles a heavier version of an electron. It carries the same electric charge but has much greater mass. It is unstable. A free muon eventually decays into an electron, one neutrino and one antineutrino. It would be misleading to imagine that the muon contains a small electron and two neutrino particles waiting to escape. The muon is an excitation of the muon field. During the decay, interactions involving other fields produce the new excitations. The final electron is not a hidden component that survived inside the muon. It appears as part of the field transition. This is common in particle physics. The products of a decay need not be internal pieces of the original particle. The process is closer to one permitted state changing into another permitted state. Radioactive decay follows the same broad principle at the level of atomic nuclei. A nucleus in an unstable arrangement can change into another nucleus while emitting particles or radiation. In some forms of radioactive decay, a neutron inside the nucleus changes into a proton while an electron and an antineutrino are produced. The emitted electron was not orbiting inside the nucleus before the decay. It is created during the interaction. The relevant fields change state. Electric charge remains balanced, and energy and momentum are shared among the products. This distinction became important in the history of physics. Early attempts to imagine the nucleus as containing all particles later emitted during decay created serious difficulties. Quantum field theory provides a cleaner description because particles can be produced when fields interact. Particle accelerators make these processes visible on a larger experimental scale. Beams of particles are accelerated to high energies and brought into collision. The incoming particles carry energy in their mass and motion. When they interact, the fields can be excited in many possible ways. The collision may produce a collection of particles far more massive than the original particles considered separately. There is no violation because the motion of the incoming beams contributes energy. That energy can become the mass and motion of new excitations. This is why colliders are sometimes described as machines that convert energy into matter. The phrase is useful, although matter and energy are not completely separate substances. A better description is that energy in one set of field, excitations, is reorganized into another set, some of which behave as massive particles. The new particles may be stable enough to reach a detector, or they may decay almost immediately. Very short-lived particles are often identified through their decay products. Researchers do not watch the particle travel across a long distance. They reconstruct its presence from the energies, directions, charges, and types of particles produced afterward. This is similar to identifying a brief event from the traces it leaves, but the reconstruction is much more precise than ordinary detective work. Physicists compare large numbers of collisions with predictions from quantum field theory. A short-lived excitation appears as a characteristic pattern in the measured data. The Higgs boson was detected in this way. It does not remain long enough to be collected in a container or photographed directly. High-energy collisions can excite the Higgs field, producing a Higgs boson. That excitation rapidly changes into other particles. Detectors measure those products, and statistical analysis reveals whether their patterns match the expected behavior. The appearance and disappearance of particles in these experiments are not rare exceptions to an otherwise permanent particle world. They are central to how the world operates at the quantum level. The particles present before an interaction are not necessarily the particles present afterward. Even in apparently empty space, the field description allows temporary effects that are sometimes discussed using the language of virtual particles. This term requires care. Virtual particles are not ordinary particles that briefly become real, break the rules, and then disappear before anyone notices. In calculations, physicists represent interactions through contributions that can be pictured using diagrams. Internal parts of these diagrams are often described as virtual particles. They help organize the mathematical calculation, but they do not behave like freely detectable particles. They do not have to satisfy all the same relationships as particles that travel into detectors. The diagrams are useful tools, not literal photographs of hidden events. Different ways of arranging the calculation can describe the same measurable process. Treating every line in a diagram as a tiny object following a definite path can create more confusion than understanding. A common popular explanation says that virtual particles borrow energy for a short time. This phrase is memorable but can be misleading. Conservation of energy is not suspended for convenient intervals. Quantum uncertainty affects how certain processes are described, but it does not provide a bank from which nature takes unauthorized loans. What experiments measure are the complete outcomes of interactions. Quantum fields fluctuate, vacuum states have structure, and calculations include intermediate contributions. None of this requires energy to be genuinely created from nothing and hidden before the deadline arrives. The vacuum can still influence physical effects. For example, the presence of boundaries can change which field states are possible in a region. This leads to measurable forces under suitable conditions. Quantum fields also affect the observed properties of particles through interactions that modify quantities such as charge and mass. These effects are sometimes described as particles surrounded by clouds of virtual particles. That image can help with intuition, but it should not be treated as a detailed mechanical picture. The deeper statement is that quantum fields interact even when no additional particles are directly detected. The distinction between real and virtual particles is therefore not a distinction between solid objects and imaginary ones. A real particle, in the technical sense, is an excitation that can appear as a detectable incoming or outgoing state. A virtual particle is part of a calculation describing an interaction and cannot be isolated and detected in the same way. The language becomes especially confusing because the word real is used in several senses. Virtual contributions have real measurable effects on experimental outcomes. They are not fictional additions to the theory. They simply are not particles that can be placed in a detector as independent objects. Another source of confusion comes from statements that particles constantly pop into and out of existence everywhere. Quantum fields in their vacuum state are not completely featureless, but the phrase can suggest a room filled with hidden particle fireworks. That is not the most reliable picture. The vacuum is the lowest energy state of the interacting fields. It has quantum properties and can influence measurements. Under certain conditions, an external source can convert what was a vacuum state into a state containing detectable particles. The source provides the required energy. Strong electric fields can produce electron and positron pairs in principle. An expanding universe can produce particles because the changing geometry affects quantum fields. Near black holes, quantum field effects lead to radiation that can be observed in the theoretical description from far away. In each case, the background conditions matter. Detectable particles are not simply appearing without a cause or energy source. The definition of what counts as a particle can also depend on the observer and the state of motion, particularly in curved or accelerated settings. This last point shows that particle number may not be an absolute property of a quantum field. In ordinary laboratory conditions, particles are well defined, and counting them is practical. In more unusual situations, two observers may not agree on whether the field is in a vacuum state or contains particles. An observer moving with constant velocity through empty space may describe the field as being in its vacuum state. An observer undergoing steady acceleration can describe the same field using a state that has thermal particle-like content. This is known as the Unruh effect. The effect does not mean one observer is correct and the other is mistaken. The concept of a particle is connected to how the field is divided into excitations relative to the observer's motion and time measurement. The underlying quantum field remains the more general object. Black hole radiation involves a related lesson. In curved space and time, the field modes that appear empty in one region or at one stage may correspond to particles for a distant observer later. The changing geometry affects how excitations are defined. These results make the field picture more than a convenient replacement for tiny objects. They suggest that particles may not be fundamental entities with an observer-independent existence in every possible situation. They can be features of a field state identified under particular physical conditions. In everyday laboratory work, this complication is usually negligible. An electron detected in a chamber is still an electron. A photon counted by a sensor is still a photon. The concept is reliable because the experimental setting provides a clear way to define and measure the excitations. The broader point is that the field does not need a fixed inventory of particles at every moment. What exists fundamentally in the theory is the quantum state of the fields. Particle descriptions become useful when that state contains identifiable excitations. This also explains why asking where a destroyed particle went can be the wrong question. The particle was not a permanent material bead that needed to travel into a hidden location. It was a pattern in a field. The interaction ended that pattern and produced others. When a photon is absorbed by your eye, the photon does not continue inside your brain as the same individual object. Its energy initiates changes in molecules in the retina. Those changes lead to electrical signals, chemical processes, and neural activity. The field excitation has been transferred into a long chain of other physical states. When food is warmed in a microwave oven, photons in the relevant frequency range interact with molecules in the food. Their energy becomes molecular motion and internal excitation. The photons are absorbed, and the food becomes warmer, often less evenly than the instruction manual confidently suggests. When matter and antimatter annihilate, their particle excitations are replaced by other excitations. When a radioactive nucleus decays, new particles can be produced. When a collider creates a heavy particle, energy from the beams becomes a short-lived pattern in a field. These are not separate tricks. They are examples of the same general principle. Fields can change state, and particle number is one feature of those states. The stability of ordinary matter does not contradict this flexibility. Most particles in everyday objects cannot simply disappear because the available interactions and conservation laws prevent it. Electrons are stable under known conditions. Protons appear to be extremely stable, and no proton decay has been confirmed. Bound systems often remain unchanged because no allowed lower energy arrangement is easily available. A book resting on a table does not flicker into photons because there is no permitted process that would transform all its matter while preserving every relevant property under those conditions. Quantum field theory allows particle creation and destruction, but it does not make every imaginable event possible. The theory is flexible and restrictive at the same time. Excitations can change, but only through specific interactions. Conservation laws, symmetries, and probabilities determine what happens. This combination gives particle physics both its variety and its precision. Once particles are understood as temporary excitations, another possibility becomes easier to consider. Perhaps the many different fields are not completely separate foundations. Perhaps electrons, quarks, photons, and other particles are different states of a deeper system. We already know that one field can support different configurations. We also know that particles can transform through interactions, and that the list of particles can change while the complete state remains consistent. The next step is to ask whether the apparent variety of particle species may come from a smaller set of underlying structures. Different particles have different masses, charges, spins, and interactions. The Standard Model describes these differences with remarkable accuracy, but many of the values must be taken from experiment. A deeper theory would try to explain why the fields have exactly those properties and why nature contains this particular collection of particles rather than another. The fact that particles can appear and disappear does not answer that question, but it removes one obstacle. If particles are not permanent pieces of substance, then different particle types may be understood as different patterns available to the same deeper framework. Their transformations may be changes of state, rather than exchanges among unrelated kinds of material. This idea appears in several areas of modern research. Some theories seek unity through extended objects whose different vibrations appear as different particles. Others begin with symmetries and treat particle types as allowed representations of a deeper structure. Some explore networks, quantum information, or entanglement as the basis from which fields and particles emerge. Before looking at those proposals, it helps to examine a simpler and already familiar possibility. Nature often produces very different visible behaviour from one underlying substance. The same material can support several phases, the same instrument can produce several notes, and the same field can support multiple kinds of activity. Particle physics may be telling us that the apparent collection of separate building blocks is really a catalogue of states, and the question now is how many of those states might belong to one deeper reality. The possibility that many particles may be different states of one deeper reality sounds ambitious, but physics has repeatedly moved in that direction. Things that once appeared unrelated have often turned out to be different expressions of the same underlying system. Electricity and magnetism were once studied as separate subjects. Electric charges produced one set of effects, while magnets produced another. Experiments eventually revealed that electric and magnetic fields are closely connected. A changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. Light itself is a travelling disturbance of this combined electromagnetic field. What looked like several different phenomena became parts of one description. A similar change happened with heat. Heat was once treated as though it might be a special substance flowing from warmer objects into colder ones. The deeper explanation showed that heat is connected to the motion and collective behaviour of matter. Temperature is not a separate ingredient placed inside an object. It describes the statistical condition of many microscopic components. These examples do not prove that all particles come from one source, but they show why physicists take unification seriously. A complicated list of separate things can sometimes be replaced by a smaller set of principles. The known particles form a surprisingly large collection. There are several kinds of quarks, several kinds of charged particles related to the electron, several neutrinos, and a group of particles associated with the fundamental interactions. There is also the Higgs boson. At first sight, this can look like a box of unrelated parts. Each particle has its own mass, charge, spin, and pattern of interactions. Some are stable, others decay almost immediately. Some respond to the strong nuclear interaction, others do not. Photons have no rest mass, while other particles are heavy enough to disappear almost as soon as they are produced. The Standard Model organises this collection with remarkable success. It tells physicists which interactions are possible and allows extremely precise predictions. Even so, it does not explain every feature of the list. The theory contains measured values that must be supplied by experiment. It does not fully explain why the electron has its particular mass, why there are several generations of matter particles, or why the strengths of the interactions have the values we observe. It gives an accurate description of the pattern without necessarily telling us why this pattern exists. A deeper theory would try to reduce the number of independent ingredients. It might show that particles now treated as separate are different states of a more basic system. Their differing properties would then arise from how that system is arranged, rather than from completely different substances. We already know that this happens in ordinary particle physics. A proton was once treated as an elementary particle. It appeared to be one of the basic components of atomic nuclei. Experiments later showed that the proton has internal structure. It contains quarks and gluons, although the word contains must be used carefully. A proton is not a small bag holding 3 hard quark balls. It is a highly active quantum system. Quark fields and gluon fields interact continuously. Additional temporary quark and antiquark contributions also affect the proton. Most of the proton's mass does not come directly from adding the masses of 3 quarks. It comes from the energy of the strongly interacting fields inside the proton. A neutron is built from the same general kinds of fields. The difference lies partly in which quark types dominate its structure. A proton and a neutron are therefore not made from completely unrelated material. They are different bound states of quark and gluon fields. Under the right interaction, a neutron can change into a proton. During this process, one type of quark changes into another, and other particles are produced. The neutron does not open and release a completed proton that had been stored inside it. The underlying field state changes. This gives us a working example of several familiar particles arising from the same deeper ingredients. Protons, neutrons, and many other particles produced in accelerators are different arrangements of quarks and gluons. Physicists call particles made from quarks hadrons. There are many kinds. Some contain combinations associated with 3 quarks. Others contain a quark and an antiquark. More complicated combinations are also possible. The long list of hadrons once created a serious problem. During the middle of the 20th century, experiments discovered so many new particles that the collection became known as a particle zoo. It seemed unlikely that nature would choose such a large number of unrelated fundamental objects. Patterns in the zoo suggested an underlying order. Quarks provided that order. Many particles could be understood as different combinations and energy states of a smaller set of components. The situation resembles the way chemistry organizes many substances using a limited collection of elements. Water, carbon dioxide, sugar, and countless other materials look and behave differently, but they arise from different arrangements of atoms. Particle physics went one level deeper by showing that many nuclear particles arise from different arrangements of quark and gluon fields. Yet quarks themselves may not be the end of the story. Electrons also remain elementary in current experiments. No internal structure has been confirmed inside an electron. The same is true for quarks as far as present measurements can determine. Calling them elementary means that experiments have not detected smaller components. It does not guarantee that they are fundamental in every possible future theory. There is another kind of unification already built into the Standard Model. The electromagnetic interaction and the weak nuclear interaction appear very different at ordinary energies. Electromagnetism acts over long distances. It holds atoms together, allows chemistry to occur, and produces familiar effects involving light, electricity, and magnetism. The weak interaction operates over extremely short distances and participates in certain forms of radioactive decay. At higher energies, however, these two interactions are described as parts of one electro-weak system. Their apparent differences emerge as the universe settles into a lower energy state. The Higgs field plays an important role in this separation. At sufficiently high energies, the underlying symmetry between the interactions is more apparent. As conditions change, the Higgs field takes on a particular non-zero state throughout space. This changes how some of the force-carrying fields behave. The photon remains without rest mass, while the particles that carry the weak interaction become massive. The forces then appear very different at the energies we normally experience. This is an important example because the deeper theory does not merely place two forces beside each other. It treats them as related parts of one structure. Their difference depends on the state of the fields. A comparison with a material changing phase can help. Water can appear as ice or liquid. The molecules are the same, but the large-scale behavior changes because they are arranged differently. Ice has a rigid structure. Liquid water can flow. The visible difference does not require two completely separate substances. The electroweak transition is much more complicated than water freezing, but both cases show how a system can have one underlying set of rules while displaying different behavior in different states. This idea is called symmetry breaking. The phrase can sound as though a physical law has been damaged. Nothing is broken in that sense. The underlying equations may retain a symmetry, even when the state of the system does not display it clearly. A round table provides a simple comparison. The table itself has no preferred direction. A person sitting at it must choose one seat. Once that seat is chosen, the arrangement no longer looks the same in every direction, even though the table has not lost its symmetry. In a physical system, the laws can allow many equivalent states. When the system settles into one of them, some of the original symmetry becomes hidden. Particles that were related in the more symmetric description can acquire different properties. The universe may contain several examples of this process. At very high energies, particle types and interactions that now look separate may have been more closely unified. As the early universe expanded and cooled, fields may have settled into states that separated the interactions and gave particles their current properties. This does not mean all differences are superficial. An electron and a photon behave differently in every ordinary experiment. One carries electric charge and has mass. The other carries the electromagnetic interaction and has no rest mass. They are distinct excitations. The unifying possibility is that their differences may be determined by one deeper framework rather than by entirely independent origins. They could be different allowed states of the same basic structure, just as several notes can come from one instrument without becoming the same note. The instrument comparison must be handled carefully. A violin exists in space and is made from matter. A fundamental physical system would not necessarily resemble a physical object with strings and wood. The useful point is that one system can support several distinct modes, each with its own behaviour. Quantum fields already work this way to some extent. A field can be excited with different energies and patterns. Interacting fields can mix, which means the particles observed in experiments may be combinations of more basic field components. Neutrinos provide an especially interesting example. There are several known kinds of neutrino associated with different particle interactions. A neutrino produced in one form can later be detected in another form. This phenomenon is called neutrino oscillation. The process does not mean that a tiny object changes its label while travelling. The neutrino state is a combination of states with slightly different masses. Those components develop differently as they move, changing the probability of which neutrino type will be detected. The neutrino created at the beginning and the neutrino detected later are connected through the evolution of the underlying quantum state. The familiar particle categories do not always correspond to a single simple component. A related kind of mixing occurs among quarks. The quark states that participate in the weak interaction are connected to the mass states through a structured pattern. Once again, the particle labels used in one kind of interaction do not align perfectly with the labels used in another part of the theory. These examples show that particle identity can depend on which property is being measured. The universe does not always provide one collection of completely separate boxes with a particle assigned permanently to each box. Sometimes the most useful particle description changes with the situation. One basis is useful for discussing mass. Another is useful for discussing a particular interaction. The deeper quantum state remains consistent while our particle categories reveal different aspects of it. Materials studied in laboratories offer even clearer examples of one system producing many effective particle types. A solid contains large numbers of electrons and atomic nuclei. Their collective behaviour can produce excitations that move through the material as if they were particles. Some of these effective particles carry energy through the vibration of a crystal. Others describe organised changes in magnetic alignment. Still others act as though they carry electric charge or unusual quantum properties. These excitations are not added to the material from outside. They arise from the coordinated behaviour of the underlying components. Different patterns produce different effective particles. A crystal can therefore contain a whole collection of particle-like entities, even though its basic ingredients are ordinary atomic nuclei and electrons. The material and its state determine which excitations can exist. This gives physicists a useful model for thinking about deeper reality. The particles we currently call fundamental could be similar to collective excitations in an unknown underlying system. Their properties might come from the organisation of that system. There is an important difference. Laboratory quasi-particles require a material background made from known particles. If electrons themselves are emergent, the deeper structure cannot simply be another ordinary material made from electrons. The explanation must eventually avoid assuming the very particles it is trying to explain. The deeper system might not look like matter at all. It could be a network of quantum relationships. It could involve extended structures. It might be based on abstract symmetry rules that determine the possible excitations. It may even require a concept that has not yet been developed. This is one reason the phrase "one deeper reality" should not be confused with one hidden physical substance. The search is not necessarily for a universal fluid-filling space. Earlier physicists considered ideas of that kind when trying to understand light, but experiments and relativity showed that a mechanical medium was not required. A deeper reality could be a set of relations or a quantum structure from which familiar space, fields and particles emerge together. Modern theoretical physics contains examples where two very different descriptions lead to the same measurable results. One description may involve particles interacting strongly. Another may use different fields that interact weakly. What looks complicated in one language can look simple in another. These relationships are called dualities. A duality suggests that two apparently different theories may be alternative descriptions of the same underlying physics. This creates an unexpected problem for the idea of fundamental ingredients. If two descriptions are equally complete but use different basic objects, which objects are truly fundamental? Perhaps neither collection deserves that title by itself. The deeper reality may be what both descriptions share, even if it is not represented as a familiar object in either one. A map offers a limited comparison. A city can be represented by a street map, a rail map, or a map of electrical systems. Each one uses different lines and symbols because each answers different questions. It would be a mistake to claim that the city is fundamentally made from whichever lines appear on one map. Physical dualities are much stronger than ordinary map choices because they can connect complete mathematical theories. Still, the comparison shows how several descriptions can organize the same reality, using different apparent building blocks. This possibility encourages caution. Fields may be fundamental in the standard model, but a deeper theory could describe the same physics without treating those fields as basic. Particles may emerge in one description and disappear from another. Black hole research has made this issue particularly important. A black hole brings gravity, quantum theory, thermodynamics, and information into the same problem. Attempts to understand black holes suggest surprising connections between the geometry of space and quantum information. In some theoretical settings, a gravitational world in a region of space can be described by a different quantum theory, associated with a lower dimensional boundary. The two descriptions contain different apparent ingredients, yet they may encode the same physical information. This does not prove that our universe works in exactly the same way. It does show that space, gravity, and particles can be related in ways that are not obvious from everyday intuition. A particle moving through a region may be represented in another description by a complex pattern of quantum information. What appears to be a local object in one theory may be spread across many degrees of freedom in another. The word information here does not mean a written message or a file stored on a computer. It refers to the distinctions between possible physical states and the correlations among them. Quantum information is still physical. It cannot exist without a system whose states and relationships carry it. Some researchers suspect that these relationships may be more basic than particles. In that view, a particle is a stable pattern in the way information is organized. Its mass, charge, and spin describe how that pattern behaves and transforms. Others place greater emphasis on symmetry. Particle types can be classified by how their states respond to transformations. From this perspective, an electron is partly defined by the role it plays within a mathematical structure. This does not reduce the electron to a human idea. The transformations produce measurable consequences. They determine which interactions are possible and how probabilities change. The structure is revealed through experiments. A familiar object is usually described by what it is made from. A wooden chair is made from wood. A glass is made from a particular material. A particle may be defined less by internal material and more by its relationships, symmetries, and allowed interactions. An electron is what responds to the electromagnetic field in the electron way. It has a certain mass and charge, it follows fermionic statistics, it participates in specific interactions. There may be no smaller piece of electron substance responsible for these properties. A deeper theory could explain all these features as consequences of one underlying state or pattern. Another particle would correspond to a different stable pattern in the same structure. This idea can also explain why particle transformations follow strict rules. If particles are states of one system, a transformation is possible only when one state can change into another, while preserving the system's required properties. A musical instrument cannot produce every imaginable sound. Its structure allows certain modes. A crystal cannot support every possible collective excitation. Its arrangement determines what can travel through it. In the same way, the deeper structure of nature may allow a particular set of particles and forbid others. The standard model may therefore be a catalogue of the stable excitation patterns available at energies we can observe. Some predicted patterns have been discovered only by creating extreme conditions in colliders. Others may require energies far beyond present experiments. There may also be excitations that interact so weakly with known matter that they have escaped detection. Dark matter is evidence that additional unseen physical components affect galaxies and larger structures, although its exact nature remains unknown. It may consist of new particles, more complicated objects, or something requiring a different explanation. Dark energy presents another unresolved problem. The observed expansion of the universe suggests behavior that is not fully explained by ordinary matter and radiation. A deeper theory of fields, gravity, and vacuum structure may be needed. These mysteries remind us that the known particle collection is not a complete description of everything in the universe. The standard model does not include a quantum theory of gravity, does not identify dark matter, and does not fully explain the observed cosmic acceleration. It is therefore reasonable to ask whether its particles and fields are parts of a larger structure. Reasonable does not mean confirmed. A deeper unified reality must do more than sound satisfying. It must reproduce the successful predictions of existing theories and explain something they cannot. It must eventually provide evidence that distinguishes it from alternative ideas. Unification has sometimes worked brilliantly, but nature is not required to be simple in the way humans prefer. The known particles may arise from several distinct fundamental structures rather than one. Some apparent patterns may be accidental. A neat theory is not automatically a true theory. Physicists continue the search because the existing pattern contains clues. Particle families repeat. Forces show related mathematical forms. Symmetries connect properties that otherwise seem independent. High-energy behavior suggests that interactions become more similar under extreme conditions. The idea of one deeper reality is therefore not based only on a desire for elegance. It grows from specific relationships already found in successful theories. The task is to determine how far those relationships extend. Perhaps quarks and electrons have smaller components. Perhaps all particles are vibrational states of extended quantum objects. Perhaps fields and space emerge from entanglement. Perhaps symmetry is more fundamental than any physical object. Perhaps several of these descriptions are different ways of approaching the same structure. The next possibilities begin by changing the form of the supposed building block. Instead of a point particle, some theories use an extended object. Instead of assigning every particle an independent origin, they treat mass, charge, and force as consequences of vibration and symmetry. These proposals attempt to explain why the universe offers the particular particle states we observe. They also try to include gravity without treating it as an unrelated addition. That brings us to strings, hidden dimensions, and the role of symmetry in deciding what kinds of particles a deeper system is able to produce. That brings us to strings, hidden dimensions, and the role of symmetry in deciding what kinds of particles a deeper system is able to produce. The first change made by string theory is simple to state. Instead of treating the most basic objects as points with no size, it treats them as extremely small extended objects. These objects are called strings because they have length, although they are not strings made from ordinary material. They are not tiny pieces of thread floating inside space. They are proposed quantum objects whose different states appear to us as different particles. A point particle has no internal shape that can vibrate. It can have properties such as mass, charge, and spin, but the theory must specify those properties for each particle type. A string has different possible patterns of vibration. Each pattern can behave like a particle with a particular set of properties. The usual comparison is a musical string. One violin string can produce several notes depending on how it vibrates. The notes are not made from different kinds of string. They are different modes of the same object. In string theory, an electron, a photon, and other particles could correspond to different quantum modes of a fundamental string. This comparison explains the central idea, but it can also create the wrong picture. A violin string vibrates through ordinary space, and its motion pushes the surrounding air. A fundamental string would not need air, wood, or an external instrument. Its vibrations would be changes in its quantum state. The word vibration is being used because the mathematics has patterns that resemble the modes of an extended object. If this proposal is correct, the particle collection would no longer be a collection of unrelated basic ingredients. There would be a more limited kind of underlying object with many possible states. The differences between particles would come from the way the string is excited. One mode might behave as a particle with electric charge, another might have no charge, one might be massive, while another might have no rest mass. Their spin and interaction patterns would also depend on the string state. This is an appealing form of unification because it replaces many basic particle types with one deeper structure. It does not say that all observed particles are the same in experiments. An electron still behaves differently from a photon. The claim is that the difference may be similar to the difference between two modes of one system, rather than the difference between two independent substances. Strings can be open or closed. An open string has two ends. A closed string forms a loop. Different versions of string theory use these possibilities in different ways. One especially important result appears among the possible states of a closed string. The theory naturally includes a massless excitation with the properties expected of a quantum particle associated with gravity. Physicists call the hypothetical quantum carrier of gravity the graviton. This was a major reason string theory attracted attention. Quantum field theories can describe the electromagnetic, weak and strong interactions very successfully. Gravity is harder to include using the same methods at extremely high energies. Straightforward calculations produce quantities that cannot be handled in the usual way. An extended string changes the interaction. Point particles interact at exact locations. When physicists calculate processes involving quantum gravity, concentrating everything at a point contributes to severe problems. A string spreads the interaction over a tiny length. This can soften some of the troublesome behaviour. The theory does not simply add a graviton by hand. A graviton-like state appears as part of the permitted string vibrations. If a theory begins with strings, quantum gravity seems to come with them. That result does not prove that strings exist. It shows that the framework has a structure capable of including gravity and particle physics together. A successful final theory would still have to reproduce the detailed behaviour of the standard model, explain the universe we observe, and make predictions that experiments can test. Strings would need to be incredibly small. The natural length associated with quantum gravity is far below the scale that current particle accelerators can examine directly. At ordinary energies, a string would look like a point because its extension would be too small to resolve. This is similar to looking at a thin cable from a great distance. It may appear to be a line with no visible thickness. Moving closer reveals another dimension. With fundamental strings, even our most powerful instruments may still be far too distant in the relevant sense. The small scale creates one of the main difficulties. A theory can contain beautiful mathematical ideas, but direct evidence becomes difficult when the predicted structure lies beyond experimental reach. Researchers therefore look for indirect effects, such as unusual particle properties, patterns in cosmology, or deviations from existing theories. No confirmed observation has shown that known particles are strings. This should remain clear throughout any discussion of the subject. String theory is a serious research program, but it is not an experimentally established replacement for the standard model. The framework also requires more dimensions than the familiar 3 dimensions of space, and one of time. Depending on the version, the theory is mathematically consistent only when additional spatial dimensions are included. This sounds immediately incompatible with experience. We move left and right, forward and backward, and up and down. We do not notice several extra directions while trying to walk to the kitchen. The proposed answer is that the additional dimensions may be compact. They may be curled into extremely small shapes at every location. We do not notice them because movement through those directions is limited to tiny scales. A simple comparison uses a long garden hose viewed from far away. From a distance, the hose looks like a one-dimensional line. An ant standing on the hose would discover another possible direction. It could move along the hose, but it could also move around its circular surface. A much larger observer may ignore that circular direction because it is too small to notice. The hose then appears to have fewer dimensions than it actually has. Extra dimensions in string theory would not necessarily be simple circles. They could have complicated geometries. Their shape would affect the possible string vibrations, and those vibrations would determine the particle properties seen at larger scales. This means the hidden geometry could help decide which particles exist. The masses, charges, and interactions of the low-energy world might depend on the way the extra dimensions are arranged. The phrase hidden dimensions can make them sound like large regions placed beyond the edge of visible space. That is not the usual proposal. They would be directions present at every point, but compacted so tightly that ordinary motion and ordinary instruments do not reveal them. The geometry creates both an opportunity and a problem. It offers a way to explain particle properties using the structure of space. However, there may be a vast number of possible compact shapes. Different shapes can produce different low-energy physics. Researchers would need to explain why our universe selected one arrangement rather than another. A theory that permits many possible universes may be difficult to test unless it provides a clear method for determining which one should resemble ours. String theory also contains objects with more dimensions than strings. These are often called branes. A string has one spatial dimension because it has length. A brane can extend across 2 or more spatial dimensions. In some models, the observable universe could be associated with a brane inside a larger dimensional setting. Certain particles and interactions might remain restricted to the brane, while gravity could behave differently because it has access to the wider space. This kind of proposal can offer explanations for why gravity appears much weaker than the other fundamental interactions. Perhaps gravity is not weak in the complete theory. Perhaps its influence is spread through additional dimensions while the other interactions remain more confined. Again, this is a possibility rather than a confirmed description. Experiments have tested gravity at short distances and searched for signs of extra dimensions. No decisive evidence has been found. The idea is useful because it demonstrates how an observed property may arise from hidden structure. Gravity might appear weak because of geometry. Particle families might arise from string states. Forces might reflect how extended objects connect and move. Symmetry is essential throughout these theories. In daily life, symmetry often means that 2 halves of an object match. Physics uses the idea more broadly. A symmetry is a transformation that leaves the physical description unchanged. A perfect sphere looks the same after it is rotated. The appearance changes from our point of view, but the sphere has no preferred direction. The laws of physics also appear to have important symmetries. An experiment performed today should follow the same basic rules as the same experiment performed tomorrow. An experiment in one location should follow the same laws as an identical experiment elsewhere. These simple statements are connected to conservation laws. When the laws do not change over time, energy is conserved. When they do not depend on position, momentum is conserved. When they do not prefer a direction, angular momentum is conserved. This connection shows that symmetry is not decorative. It controls what physical processes can occur. Particle physics uses internal symmetries that are harder to visualize. These transformations do not simply rotate an object in ordinary space. They change mathematical components of quantum fields while leaving measurable physics consistent. The interactions in the standard model are built around these symmetries. The photon, the particles associated with the weak interaction, and the gluons are connected to the symmetry structure of the fields. From this viewpoint, force-carrying particles appear because the theory must remain consistent when certain transformations are allowed to vary from one location to another. The fields required to preserve that consistency become the fields associated with interactions. This is a major reversal of the simple mechanical picture. A force is not always introduced by imagining tiny particles thrown between objects. The interaction can follow from a demand that the description respect a local symmetry. The particles then appear as excitations of the fields required by that symmetry. An electric charge, for example, is not merely a small amount of electrical substance stored inside a particle. It tells us how the particle state responds to the symmetry connected with the electromagnetism. Other charges describe how particles respond to the weak and strong interactions. These properties are defined through relationships within the mathematical structure. The word charge remains useful because it connects directly with measurements. Charged particles accelerate in electromagnetic fields. They attract or repel other charges. The deeper description explains that behavior through symmetry and field interactions. This suggests that relationships may be more fundamental than the apparent objects. A particle is partly defined by how it transforms and how it interacts. Remove those relationships, and much of what distinguishes one particle from another disappears. Mass also depends on deeper structure. Some particles acquire mass through their interaction with the Higgs field. The Higgs field has a non-zero state throughout empty space. Particles that interact more strongly with it generally acquire larger masses through the mechanism used in the standard model. This does not explain every mass value. The strengths of those interactions still have to be measured. A more complete theory might explain why each particle couples to the Higgs field with its particular strength. String theory attempts to derive such features from geometry, vibration, and symmetry. Different string modes and the shapes of hidden dimensions could determine the possible interactions. The goal is not merely to fit known numbers, but to show why the numbers could not have been otherwise within the chosen structure. Achieving that goal has proved difficult. Many possible string arrangements can lead to different low-energy results. Selecting the arrangement corresponding to our universe remains a major challenge. Symmetry can also connect matter particles with force-carrying particles. One proposal is called supersymmetry. It introduces a relationship between fermions, which include matter particles such as electrons and quarks, and bosons, which include force-related particles such as photons and gluons. In a supersymmetric theory, known particles would have partner particles with different spin behavior. A known fermion would be related to a bosonic partner, and a known boson would be related to a fermionic partner. No confirmed supersymmetric partner has been observed. If supersymmetry exists in nature, it must be hidden or broken at the energies we currently study. The partner particles may be too massive for present experiments, or the symmetry may appear in a form different from the simplest models. Supersymmetry remains important in string theory because it helps the mathematical structure remain consistent. It can remove certain unwanted states and improve the behavior of calculations. It has also been explored as a possible explanation for dark matter and for features of the Higgs field. The lack of experimental evidence has ruled out many simple versions. It has not eliminated every possible form, but it has made the search more constrained. This is an important part of scientific progress. A proposal does not remain unchanged when experiments fail to find what was expected. Models are restricted, modified, or rejected. The broad idea may continue, but specific predictions face evidence. Strings are not the only proposed hidden structure. Some theories suggest that quarks and electrons may contain still smaller components. These hypothetical components are sometimes called preons. A preon model would resemble earlier steps in particle physics. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks. Perhaps quarks and electrons also contain smaller parts. No internal structure has been detected inside quarks or electrons. High-energy scattering experiments have examined them at extremely small distances and found them consistent with point-like behavior. If preons exist, their scale must be smaller than current measurements can resolve. A preon theory would also need to explain why composite electrons and quarks appear so light and so stable. Binding smaller components usually contributes large amounts of energy, which affects the mass of the composite object. Building a realistic model is difficult. Other approaches avoid smaller components and focus on the structure of space itself. Loop quantum gravity, for example, attempts to describe geometry using quantum states associated with networks. In these models, area and volume can have discrete quantum properties. Space would not be a smooth background at the smallest scale. It would have an underlying quantum structure. The familiar continuous geometry would emerge when many microscopic elements are considered together. Loop quantum gravity is primarily a proposal about quantum space and gravity rather than a complete unification of all particle types. It shows another way in which the apparent foundations can change. Instead of placing quantum particles inside a fixed space, the theory makes space itself part of the quantum system. Related approaches use networks, causal relations, or discrete events as basic ingredients. A causal set model begins with ordered relations between events. The order records which events can influence which others. Smooth space and time would emerge only at larger scales. In these theories, particles might be patterns moving through an underlying network. Their behavior would depend on the network structure, just as waves in a material depend on the arrangement of that material. The difficulty is making the large-scale result match both general relativity and quantum field theory. The smooth space we observe is extremely regular. Any microscopic network must reproduce that regularity, while also explaining particle physics. Some proposals treat particles as topological structures. Topology studies features that remain unchanged under smooth deformation. A knot, for example, cannot be removed without cutting the loop or passing one part through another. In a field or network, stable twists, knots, or defects can behave like particles. They may move, interact, and resist decay because their structure cannot be smoothly removed. This already happens in certain materials. A defect in the arrangement of atoms or spins can behave as a stable object. The defect is not an extra piece added to the material. It is a special organization of the underlying system. A fundamental particle could conceivably be a similar stable feature of a deeper field or network. Charge might correspond to a kind of topological structure. Particle stability might follow from the impossibility of continuously removing that structure. This would explain why certain particles persist. An electron may be stable not because it is a permanent bead, but because its underlying pattern cannot unwind without violating a conserved property. No single proposal has established that known particles are topological defects of a deeper system. The concept remains useful because it offers another route from one underlying structure to several particle types. Strings, preons, quantum networks, and topological patterns are very different ideas. They should not be blended into one vague claim. Each has its own mathematics, goals, and difficulties. What they share is a willingness to treat the standard particle list as an effective description rather than the final inventory of reality. They ask whether particles are stable modes, bound states, network patterns, or symmetry structures. A successful theory would need to recover everything that already works. It must reproduce the known particle masses, charges, spins, and interactions. It must account for relativity and quantum mechanics. It must explain why violations of established principles have not been observed. It must also make new predictions. Without testable differences, a deeper description may remain mathematically interesting but experimentally undecidable. Testing these ideas is difficult because several theories reproduce ordinary physics at accessible energies. Their differences become visible only in extreme conditions. Researchers search in high-energy collisions, precision measurements, gravitational observations, and signals from the early universe. Particle accelerators can look for unexpected resonances, partner particles, signs of compositeness, or energy apparently moving into extra dimensions. So far, the standard model has remained highly successful. Precision experiments examine whether electrons have internal structure, whether known symmetries are exact, and whether particle properties differ slightly from standard predictions. Even a tiny confirmed deviation could reveal a deeper layer. Cosmology offers another route. The early universe reached energies unavailable in laboratories. Patterns in cosmic radiation, gravitational waves, or the distribution of matter might retain information about processes connected with quantum gravity or hidden structures. The challenge is that cosmic evidence can have several explanations. Researchers must separate a genuine signature of fundamental physics from more ordinary astrophysical effects. Black holes may also provide clues. They combine strong gravity with quantum fields and raise difficult questions about information. If a black hole evaporates through quantum processes, the theory must explain what happens to the information describing the matter that formed it. Attempts to solve this problem have produced some of the strongest hints that geometry and quantum information are connected. Space may not be a passive container. Its structure may depend on patterns of entanglement among quantum degrees of freedom. This possibility changes the search again. The deepest layer might not be an object, whether a point, string, or network element. It might be the organization of quantum information and the relationships among possible states. In that case, strings and particles could both be useful descriptions that emerge under different conditions. Symmetry would describe the allowed transformations of the information. Geometry would reflect how the relationships are arranged. Particles would appear as stable patterns within that organization. The idea remains speculative, but it grows from concrete results in quantum theory, gravity, and black hole physics. To understand why researchers take it seriously, we need to examine what physicists mean by information, how entanglement creates relationships that have no classical equivalent, and how those relationships might produce fields, particles, and even the space in which they seem to move. To understand why some physicists think reality may be built from information and entanglement, we first need to be careful with the word information. In everyday life, information means facts, messages, instructions, or data stored in a book or computer. In physics, the meaning is more basic. Information describes the possible states of a physical system and the differences between those states. A coin can be heads or tails. A light can be on or off. An atom can occupy one energy state or another. Each system has several possible conditions, and information tells us which condition is present. The information is not separate from the physical system. It is carried by the arrangement of matter, fields, or energy. This is why deleting information from a computer is still a physical process. The machine must change the state of its memory. Energy is used, heat is produced, and physical components are rearranged. Information may seem abstract when it appears as words on a screen, but the storage and transfer of that information always involve physical states. Quantum information applies the same idea to quantum systems. A quantum system can have possible states that do not behave like ordinary alternatives. An electron does not always have one definite classical condition that is merely hidden from us. Its state can contain several possible measurement outcomes at the same time. This does not mean the electron is secretly making several ordinary choices. The quantum state follows rules that have no exact equivalent in classical physics. When different possibilities are combined, they can reinforce or cancel one another. This produces interference, which is one of the central features of quantum theory. A quantum state can also contain correlations between systems. Two particles can be prepared in a joint state where their measurement outcomes are connected. These connections can remain even when the particles move far apart. This phenomenon is called entanglement. Entanglement is often described as a mysterious link between distant particles. That description is useful at first, but it can suggest that each particle has its own complete state and also carries an invisible communication cable. Quantum theory says something more unusual. The pair can have a definite joint state even when the individual particles do not have separate definite values for the measured properties. The information belongs to the relationship. Imagine two cards placed into envelopes. One card is red and the other is blue. The envelopes are mixed and one is sent to a distant laboratory. Opening one envelope immediately tells you the colour of the other card. This is an ordinary correlation. The colours were fixed before the envelopes were separated. You simply did not know which envelope contained which card. Quantum entanglement cannot always be explained that way. Experiments show correlations that are stronger than any theory based only on hidden predetermined values can reproduce, provided the experiments satisfy the required conditions. The measurement results are not simply revealing a complete set of instructions carried by each particle from the beginning. This conclusion was tested through experiments based on a result known as Bell's theorem. Bell showed that theories in which particles carry local hidden values must obey certain limits. Quantum mechanics predicts that entangled particles can exceed those limits. Experiments have repeatedly supported the quantum prediction. The result does not allow messages to be sent faster than light. A measurement made in one laboratory produces a result that appears random. The distant laboratory also receives a random result. The correlation becomes clear only when the two sets of results are later compared through ordinary communication. Entanglement, therefore, does not provide an instant telephone. It does show that a quantum system cannot always be divided into independent local pieces with complete individual properties. The whole state contains information that is not stored separately in either part. This is one reason some physicists suspect that relationships may be more fundamental than particles. A particle may not be a self-contained object carrying all its properties inside itself. Its state may be defined partly through its connections with other systems. The idea becomes especially important when we consider many particles. In a large quantum system, the components can become entangled in complicated patterns. Those patterns determine which collective states are possible and how the system behaves. A solid object is not merely a pile of independent atoms. Its electrons and nuclei interact. Their quantum states are constrained by one another. In some materials, entanglement contributes directly to the large-scale properties that physicists observe. Certain phases of matter cannot be described by examining one particle at a time. Their important features are spread across the system. The order belongs to the pattern of relationships rather than to any single component. This gives researchers examples of how apparently new physical behavior can emerge from information shared across many degrees of freedom. A quasi-particle moving through a material can arise from a collective quantum state. It may behave as though it were an individual object, even though its existence depends on the organization of the entire system. If ordinary laboratory materials can produce particle-like excitations from collective information, perhaps the particles of the standard model arise in a related way from a deeper quantum structure. The comparison is not proof, but it provides a concrete mechanism for emergence. The more radical proposal is that space itself may depend on entanglement. In the usual picture, space exists first. Particles occupy positions within it. Two particles can then become entangled across a distance. The distance appears to be a basic fact, while entanglement is an additional relationship between objects already placed in space. Some theories reverse that order. The network of quantum relationships comes first, and the geometry of space emerges from the way those relationships are arranged. Distance would then be a large-scale description of how strongly different parts of the deeper system are connected. Two regions with strong quantum connections may appear close together. Regions with weaker connections may appear farther apart. The smooth space we experience could be an effective representation of a much more complicated pattern of entanglement. This idea developed partly through research on black holes and quantum gravity. Black holes force physicists to consider gravity, quantum fields, thermodynamics, and information at the same time. A black hole has a boundary called an event horizon. Once matter passes beyond it, signals from that matter cannot return to a distant observer. Classical general relativity describes the black hole using only a small set of properties, such as mass, electric charge, and rotation. This creates a question. A complicated object can fall into a black hole carrying a large amount of detailed information. If the black hole is described by only a few visible properties, where does the rest of the information go? The problem becomes more serious when quantum effects are included. Black holes are expected to release radiation and gradually lose mass. If the black hole eventually disappears, the radiation must somehow account for the information that entered it. Early calculations suggested that the radiation might be completely thermal. Thermal radiation would depend mainly on the black hole's basic properties and would not obviously preserve the detailed information about everything that fell inside. If the information were permanently destroyed, quantum mechanics would require a major change. Standard quantum theory says that the evolution of an isolated system preserves information in a precise sense. The final state may be extremely complicated, but it must remain connected to the initial state. The conflict became known as the black hole information problem. It is still an active subject, but many physicists now expect that information is preserved. The challenge is explaining how the information is encoded in the outgoing radiation, and how the interior description fits with the exterior one. Black hole thermodynamics gave an important clue. A black hole has an entropy, which measures the number of microscopic states that could correspond to its large-scale properties. Surprisingly, this entropy is related to the area of the event horizon, rather than the volume inside the black hole. For ordinary systems, the amount of information that can be stored usually increases with volume. A larger box can hold more particles and more possible arrangements. A black hole suggests that the maximum information associated with a region may instead scale with its boundary area. This led to the holographic principle. The name comes from a hologram, where information about a three-dimensional image is stored on a two-dimensional surface. In theories of gravity, the proposal is that all the physical information inside a region may be represented by degrees of freedom associated with its boundary. This does not necessarily mean the universe is a projection in the everyday sense. It means that a description using gravity in a volume may be equivalent to another description without gravity on a lower dimensional boundary. One of the strongest examples appears in a mathematical relationship known as gauge-gravity duality. In certain theoretical settings, a gravitational theory in a higher dimensional space is equivalent to a quantum field theory, defined on the boundary of that space. The two theories look very different. One contains gravity and a curved interior geometry. The other contains quantum fields without gravity in a lower number of dimensions, yet the physical information can be translated between them. A particle moving through the gravitational interior may correspond to a complicated pattern in the boundary theory. A black hole may correspond to a hot quantum state. Changes in geometry may correspond to changes in entanglement. This duality is best understood in specially structured model universes rather than the exact universe we observe. Even so, it provides a real mathematical example where space, gravity, and particles can emerge from a different quantum description. The result changes the meaning of fundamental. In the interior description, A particle may seem like a basic object moving through space. In the boundary description, the same particle is represented by a pattern involving many quantum degrees of freedom. Neither description is necessarily more real. They may be two complete languages for the same physics. This is similar to describing sound as a pressure wave or as a collection of quantized vibrations. The useful concepts depend on the question being asked. The deeper reality may not correspond exactly to the objects that appear most natural in either description. Entanglement plays a major role in the connection between the boundary theory and the interior geometry. Calculations show that the amount of entanglement between parts of the boundary system is related to geometric areas in the gravitational description. When the entanglement pattern changes, the geometry can change. Reducing certain connections can cause parts of the emergent space to become separated. Increasing the connections can make the geometry more continuous. This suggests that connected space may depend on quantum entanglement. Remove the relevant entanglement, and the smooth interior may no longer exist in the same form. A simple network comparison can help. Imagine many points connected by lines. The number and strength of the connections determine how easily one part of the network can influence another. 2 points may be far apart on a sheet of paper but closely connected within the network. Another pair may appear nearby but have no direct connection. The effective distance inside the network depends on the relationship pattern rather than the drawing. In a theory where geometry emerges from quantum information, ordinary distance may work in a similar way. The actual quantum networks are not simple diagrams drawn in a hidden space. If space itself is emergent, the network cannot be assumed to sit inside an earlier physical space. The connections define the structure from which spatial ideas later appear. This is difficult to imagine because every mental picture already uses space. We picture points, lines, surfaces, and distances. A fundamental description without space may be mathematically clear, while remaining impossible to visualize directly. Physics has faced this problem before. Quantum states cannot always be represented as objects moving through ordinary three-dimensional space. Researchers rely on mathematical structures and experimental predictions rather than insisting that every concept match a familiar image. Quantum error correction has provided another connection between information and emergent space. Error-correcting codes protect information by spreading it across many physical components. No single component contains the full message. If some components are lost or damaged, the information can still be recovered from the remaining system. Certain models of holography have a similar structure. Information associated with a region of the gravitational interior is distributed across the boundary theory. The same interior information may be reconstructed from different portions of the boundary under suitable conditions. This suggests that space may be organized like a quantum error correcting code. The geometry would not simply store information at one point. It would encode that information non-locally across many degrees of freedom. Such an arrangement could explain why the interior appears stable even when small parts of the boundary description are disturbed. The physical information is protected by redundancy. Again, this is not the same as saying the universe runs on a computer. Quantum error correction is a mathematical and physical principle. It can appear in natural systems without anyone programming them. The computer comparison can be useful only in a limited way. A computer simulation has hardware outside the simulated world. There is no evidence that our universe depends on an external machine or programmer. The information-based proposals in physics do not require that idea. They ask whether the most basic description of nature concerns possible states, transformations and correlations rather than tiny substances. The phrase reality is, information can also be misunderstood. Information normally tells us something about a system. It is reasonable to ask what the information is information about. If the answer is always another deeper physical object, then information may not be fundamental after all. Some researchers respond that physical reality may consist of relations among possible events. The information is not a description placed on top of an independent substance. The distinctions and relationships are the structure. Others think information is only a useful language. Fields or another physical system may still be fundamental, while information describes our knowledge of its states. The difference between these views is partly philosophical, but it can become physical if one approach produces new testable predictions. Entanglement alone does not automatically create particles. A detailed theory must explain how specific particles arise, why they have particular masses and charges, and why they follow the symmetries observed in experiments. Researchers use tools called tensor networks to study how large quantum states can be built from smaller connected parts. A tensor network is a mathematical structure that records how local pieces of quantum information are linked. Some tensor networks produce patterns resembling curved geometry. Their structure can organize information across several scales, from short-distance details to larger collective behavior. These networks are useful in condensed matter physics, quantum computing, and studies of holography. They demonstrate how geometry-like organization can arise from entanglement patterns. They do not yet provide a complete model of our universe. Real space and time must obey general relativity at large scales. The theory must also include the standard model particles, explain cosmic history, and account for observations with high precision. Time presents an additional challenge. It is one thing to suggest that spatial distance emerges from entanglement. It is harder to explain the passage and direction of time. Quantum information changes through interactions. Entanglement can grow as systems become more correlated. This growth is related to thermodynamics and the increase of entropy. Some researchers investigate whether the direction of time is connected to the way quantum information spreads. A system that begins in a relatively simple state can evolve into a highly entangled one. Information that was once accessible in a small region becomes distributed across the entire system. Recovering the original local details becomes extremely difficult, even though the total quantum evolution may preserve the information. This process is called scrambling. Black holes appear to be extremely effective scramblers. Information entering a black hole may be rapidly mixed among its microscopic degrees of freedom. Scrambling does not destroy information. It hides simple information inside complicated correlations. A cup of hot tea cooling in a room provides an ordinary example of information becoming harder to recover. Energy spreads into the air, the cup, and nearby surfaces. The microscopic laws may preserve the complete state, but reconstructing the original arrangement is practically impossible. At the quantum level, entanglement makes this spreading more complete. The state of one part cannot be described independently from the rest. This may help explain why the world appears classical at large scales. A small quantum system interacts with its environment and becomes entangled with it. Information about delicate quantum interference spreads into countless environmental degrees of freedom. The process is called decoherence. It does not select one final outcome by itself in every interpretation of quantum mechanics, but it explains why interference between large-scale alternatives becomes extremely difficult to observe. A dust particle, measuring device, or human body constantly interacts with light, air molecules, and surrounding matter. These interactions spread information about its position into the environment. The object then behaves as though it has a stable classical location. The familiar world of separate objects may therefore emerge from the distribution of quantum information. At the fundamental level, the state is entangled. At the practical level, environmental records make certain properties appear definite and persistent. Particles may emerge through a related process. A quantum field supports many possible states, but interactions with detectors produce stable records corresponding to particle events. The particle is not necessarily a tiny object following a complete classical path. It is a recurring pattern in how quantum information is created, transferred, and recorded. This is consistent with the field picture discussed earlier. A field excitation spreads according to quantum rules. A detector interacts locally and records a discrete event. Information about that event then spreads into the detector, its electronics, and the environment. After the record has been amplified, the particle detection becomes an ordinary fact. A light appears on a screen. A current moves through a circuit. Data is stored. The quantum event has produced a stable information pattern at a larger scale. From this viewpoint, particles may be identified by the kinds of information they preserve during interactions. An electron carries a fixed electric charge. It follows fermionic statistics. It transforms according to specific symmetries. These are reliable structural features of the quantum state. The electron may not need an internal material core. Its identity as a particle type may consist of a stable set of relationships and transformation rules. This approach is close to the symmetry-based view. A particle is defined by how it changes under rotations, motion, and internal transformations. Quantum information adds attention to how the state is connected with other states and how its properties are encoded. The deeper system could contain patterns that remain stable under allowed transformations. Those patterns would be recognized as particles. Different particles would correspond to different stable ways of organizing information. A useful comparison comes from a whirlpool. The water molecules constantly change, but the organized motion persists. The whirlpool has location, size, direction, and lifetime. It can interact with other patterns in the water. The whirlpool is not an extra substance added to the liquid. Its identity comes from a stable relationship among motions. A particle may be a much more fundamental quantum version of this idea. The difference is that a whirlpool exists in known water and space. A particle emerging from information would arise from a structure deeper than fields and perhaps deeper than space itself. There may be no underlying material that resembles anything familiar. This is where caution becomes important. Information and entanglement have produced powerful insights, but they have not yet replaced the standard model with a complete tested theory. Quantum field theory remains the best established description of known particles. General relativity remains the best established description of gravity on large scales. Information-based approaches are attempts to understand how these successful theories fit together. Their strongest support comes from mathematical relationships, black hole physics, quantum computing, and models of many body systems. A final theory would need to explain why the standard model has its exact symmetry structure. It would need to produce electrons, quarks, photons, and other particles with the measured properties. It would need to recover smooth space and time. It would also need to make predictions that can be compared with observations. There is no guarantee that the word information will appear in the final answer. It may be one step toward a deeper description. Future physicists may find a structure that makes both particles and information look emergent. This has happened with other concepts. Temperature once seemed fundamental to the experience of heat, but it emerged from statistical behavior. Particles now appear fundamental in experiments, but quantum field theory describes them as excitations. Fields may in turn emerge from a deeper structure. At each level, the earlier description remains useful. Temperature does not become meaningless because molecules exist. A photon does not become unreal because it is an excitation of a field. Space would not become useless because it emerges from entanglement. Emergence means that a stable and effective description appears when many deeper elements are organized in the right way. It does not mean the resulting objects are false. The question is therefore not whether particles exist. They clearly appear in experiments and produce reliable effects. The question is what kind of existence they have. They may be basic objects. They may be modes of strings. They may be patterns in quantum fields. They may be topological structures in a network. They may be stable arrangements of quantum information. Several of these descriptions may even refer to the same underlying reality from different directions. The next step is to bring these possibilities together without pretending that one has already been confirmed. We need to ask what physicists actually mean by fundamental, whether the search for a final building block is based on the right assumption, and how an emergent particle can remain completely real even when it is not the deepest thing in the universe. We need to ask what physicists actually mean by fundamental, whether the search for a final building block is based on the right assumption, and how an emergent particle can remain completely real Even when it is not the deepest thing in the universe, the word fundamental usually refers to something that is not explained as a combination or consequence of anything simpler. In the standard model of particle physics, electrons, quarks, neutrinos, and several force-carrying particles are treated as fundamental because no smaller components have been detected inside them. They're represented by quantum fields, and their properties are included in the basic structure of the theory. This is a practical and scientific use of the word. It means fundamental within the theory and within the range of present evidence. It does not necessarily mean fundamental for all time or at every possible scale. Atoms were once called fundamental because no smaller structure was known. Later, experiments revealed electrons and atomic nuclei. Nuclei were then understood as collections of protons and neutrons. Protons and neutrons were later shown to have quark and gluon structure. At each stage, the earlier objects remained real. Atoms did not stop existing when nuclei were discovered. Protons did not become imaginary when quarks were introduced. The new theory explained why the older objects had the properties they did. An atom is now understood as a stable quantum system formed from a nucleus and electrons. It remains useful in chemistry because chemical behavior depends on atomic structure. A chemist does not need to replace every discussion of oxygen with a detailed account of quark fields. The same may be true of particles. An electron may be a genuine and stable feature of nature, while still having a deeper explanation. Its mass, charge, and behavior could arise from a structure that is not visible at the energies available to us. There are several ways this could happen. The electron might contain smaller components, although no evidence for such components has been found. It might be a mode of an extended object, as proposed in string theory. It might be a stable topological pattern in a deeper field or network. It might be an excitation that emerges from quantum information and entanglement. It is also possible that the electron field is fundamental, and there is no deeper mechanical structure beneath it. Physics does not currently have enough evidence to select a final answer. The phrase, "what lies beneath," can create the image of layers arranged by physical size. We imagine opening a particle and finding smaller objects inside it, then opening those objects and continuing downward. That pattern has worked before, but it may not continue indefinitely. A deeper explanation does not have to involve something smaller in the ordinary spatial sense. Quantum fields are not small objects hidden inside particles. They extend through space. Symmetries are not components that can be removed with a sufficiently delicate instrument. Entanglement is a relationship within a quantum state. The next level may be deeper because it explains more, not because it is physically smaller. This changes the kind of question we need to ask. Instead of asking what material a particle contains, we may need to ask what structure allows that particle to exist. We may ask why the electron field has its particular symmetry, why its excitations have a fixed charge, and why the electron is stable. A complete answer could involve relationships rather than parts. It could show that the properties of the electron follow from the way a deeper system transforms. The particle would then be defined by its role in the structure. This is already partly true in modern physics. Particles are classified by mass, spin, charge, and their responses to symmetries. An electron is not recognized by its appearance. It is recognized by the stable pattern of properties it carries and the interactions in which it participates. No one has seen an electron as a small visible object. Experiments detect the effects associated with the electron states. A detector records energy, electric charge, momentum, and other measurable quantities. The theory connects those events to an excitation of the electron field. This does not weaken the evidence for electrons. Scientific reality is not limited to objects that can be viewed directly. Magnetic fields, radio waves, atoms, and distant planets can all be studied through their effects. The question is whether the electron field itself requires an explanation in terms of something more basic. One reason physicists expect a deeper theory is that the standard model contains many values that are measured rather than derived. The masses of the particles are examples. the strengths of several interactions must also be determined experimentally. The theory tells us how those quantities affect physical processes, but it does not fully explain why they have the particular values observed in nature. A deeper framework might show that these values result from geometry, symmetry, or another underlying structure. There is no guarantee that such an explanation exists. The values may be basic facts. They may also depend on the state of the early universe rather than on a unique mathematical requirement. This distinction matters. A law can determine which possibilities are allowed without selecting one exact outcome. Water molecules follow fixed physical rules, but water can freeze into many possible patterns. The detailed structure of each piece of ice depends on its history and environment. The laws of a deeper theory might permit many different low-energy universes. Our observed particles and forces could depend on which state the universe entered as it cooled. If that is true, asking why an electron has its exact mass may be similar to asking why a particular crystal formed with one arrangement rather than another. The answer would involve both fundamental rules and historical conditions. Another reason to expect deeper physics is that the standard model does not include gravity in the same quantum framework. General relativity describes gravity as the curvature of space and time. Quantum field theory describes the other known interactions using fields and quantum states. Both theories are extremely successful in their proper domains. The problem appears when strong gravity and quantum effects become important at the same time. The early universe is one such setting. Black holes provide another. In these conditions, treating space and time as a smooth classical background may no longer be sufficient. A deeper theory must explain quantum fields and quantum geometry together. It may reveal that particles and space emerge from the same underlying structure. If space is emergent, the phrase a particle located in space becomes a large-scale description. The particle and the space containing it may both arise from a network of more basic relationships. This is not as unusual as it first sounds. In a solid, vibrations and the medium through which they move are connected. A sound wave cannot be separated completely from the material that supports it. The wave and the medium belong to one physical system. A theory of quantum gravity might show that matter excitations and geometry are also inseparable at the deepest level. What we call a particle could be a disturbance in a structure that also produces distance, duration, and gravity. Some approaches begin with extended objects, others begin with networks, events, or algebraic relationships. Some try to describe the universe through quantum information. None has yet produced a complete, experimentally confirmed picture. This uncertainty is not a failure of science. It marks the edge of what current evidence can establish. Physics becomes difficult near this edge because several theories can agree with all available measurements. If two models produce the same predictions at ordinary energies, experiments cannot distinguish them until a situation is found where their predictions differ. That situation may require much higher energies, much greater measurement precision, or observations of unusual astronomical events. It may also require a new experimental idea. Particle accelerators search for signs of deeper structure by colliding particles at high energies. If an electron or quark contains smaller parts, sufficiently energetic collisions might reveal a change in scattering behavior. The particle might stop looking point-like. So far, no confirmed internal structure has appeared. Electrons and quarks continue to behave as point-like entities within the resolution of current experiments. This does not prove they are truly points. It sets a limit on how large any hidden structure could be. Experiments also search for new particles. Some deeper theories predict heavy partners of known particles, extra force carriers, or signs of additional dimensions. No discovery has yet provided decisive evidence for the major proposed frameworks. Precision measurements offer another path. A deeper theory can produce tiny changes in familiar quantities. The magnetic behavior of particles, the rates of rare decays, or the relationships among interaction strengths may differ slightly from standard predictions. A reliable disagreement could reveal new physics even when the deeper objects cannot be produced directly. The challenge is that precision experiments are complicated. A result may be affected by detector behaviour, uncertainties in the calculations, or unknown influences from ordinary physics. Independent confirmation is essential. Astronomy expands the search beyond laboratories. Cosmic rays reach energies that are difficult to reproduce on Earth. Neutron stars contain matter under enormous pressure. Black hole collisions create strong gravitational waves. The early universe left patterns in radiation and the distribution of galaxies. These environments may reveal effects connected to deeper particle structure or quantum gravity. They also involve complex astrophysical processes, so clear interpretation is rarely easy. Dark matter remains one of the strongest signs that known particle physics is incomplete. Galaxies and galaxy clusters behave as though they contain more gravitating matter than we can see. The standard model does not provide an obvious particle that accounts for all the observations. Dark matter may consist of one or more new particle types. It could also involve compact objects or a modification of our understanding of gravity, although many possibilities are strongly constrained by evidence. If dark matter particles are discovered, the known particle list will expand. That discovery may provide clues about a deeper unifying structure. Dark energy is another major gap. Observations show that the expansion of the universe is accelerating. A simple explanation uses a constant energy density associated with empty space, but its observed value creates difficult theoretical questions. A deeper understanding of quantum fields and vacuum structure may be needed. The same theory that explains why particles emerge could also help explain why apparently empty space affects the universe on the larger scales. This connection reminds us that particle physics is not only about very small objects. The behaviour of quantum fields influences the history and structure of the entire cosmos. The word building block may therefore be too limited. A building block suggests a solid piece that can be stacked with other pieces. Known particles do not behave like that. They are quantum excitations, and many of them are unstable. They can be created and destroyed. They can become entangled. Their identity cannot always be followed through an interaction. A better comparison may be a set of stable patterns allowed by the laws of a system. A language is not built from physical blocks. It is organized through sounds, grammar, and relationships. A small number of rules can produce an enormous number of sentences. The sentences are real expressions, but they are not the basic substance of the language. Particles may be expressions permitted by a deeper physical grammar. Their properties could reflect the rules that determine which patterns are stable and how those patterns interact. This comparison should not be taken too far. The universe is not literally speaking, and physical laws are not written instructions. The point is that structure and relationship can be more basic than object and material. A particle could be defined by what transformations leave it recognizable. It could be stable because certain conserved properties prevent it from disappearing. It could interact in specific ways because the symmetry structure allows only those interactions. The electron provides a clear example. It carries electric charge. Because electric charge is conserved, the lightest particle carrying that charge cannot simply decay into particles with no charge. The electron's stability is therefore connected to its position in the structure of the laws. It does not need to be made from indestructible electron substance. A proton may also be stable because of conservation rules, although some theories allow proton decay over extremely long periods. Experiments have searched for such decay and have not confirmed it. If proton decay were observed, it would show that quarks and other particles participate in a deeper unified interaction. It would also reveal that a familiar and apparently permanent component of matter is only a long-lived state. Longevity can easily be confused with fundamentality. A mountain may last for millions of years without being fundamental. A proton can remain stable for an enormous time, while still being a composite quantum system. An unstable particle can be important without lasting long. The Higgs boson exists for only a tiny interval before decaying, yet its discovery confirmed a central part of the standard model. The importance of a particle does not depend on whether it is permanent. It depends on the role of its field and the evidence for its effects. This helps answer whether emergent particles are real. A thing can be real, even if it exists only as a pattern. A wave is real because it carries energy and changes other systems. A hurricane is real because it produces measurable pressure, wind, and damage. A living organism is real, even though the atoms in its body are replaced over time. Reality does not require being fundamental. It requires having stable, measurable effects within a reliable description. The chair beneath you is not fundamental. It is made from molecules, atoms, nuclei, and electrons. At another level, it is a pattern maintained by chemical bonds and quantum restrictions. It remains completely real when you sit on it. Its emergent nature does not make the consequences of missing the chair any less immediate. Particles can be real in the same way. An electron leaves tracks in detectors, carries current through wires, forms atoms, and produces chemical bonds. A deeper explanation would not erase any of those facts. This principle is sometimes called effective reality. At a given scale, certain objects and rules provide the best description. Fluid mechanics describes water without tracking every molecule. Thermodynamics describes heat without calculating every atomic collision. Biology describes cells without beginning with particle interactions. Each level has concepts that remain useful because the deeper details combine into stable, large-scale behavior. An effective theory does not mean a careless approximation. Some effective theories are extraordinarily precise within their range. The standard model itself may be an effective theory that works extremely well below a certain energy. At higher energies, new structures may appear. The standard model would then remain valid as the low energy limit of a broader theory. General relativity may also be an effective description. Smooth space and time could emerge from quantum relationships at larger scales. The familiar geometry would remain accurate wherever the microscopic details average out. This layered view of nature avoids the idea that only the deepest level is real. If only fundamental things counted as real, almost everything in ordinary experience would have to be dismissed. Tables, weather, cells, animals, languages, and memories are all organized patterns. The deepest theory would not replace these things. It would explain how they are possible. There is still a difficult question. Must there be a final level? Perhaps physics will eventually find one mathematical structure from which all particles, fields, space, and time follow. That would be a theory with no known deeper explanation. Another possibility is that explanations continue through several levels without a final set of building blocks. Each level could emerge from another, with no simple endpoint. There may also be a closed structure in which several concepts explain one another. Space may emerge from entanglement, while the meaning of entanglement depends on the structure of quantum states, which is connected to the symmetries that also define matter. In that kind of theory, asking which single ingredient comes first may be the wrong question. The foundation could be a consistent network of relationships rather than one object placed at the bottom. A circle has no first point unless we choose one for convenience. A physical theory might have a similar organization, with several descriptions connected so completely that none has absolute priority. Dualities in modern theoretical physics give some support to this possibility. Two theories can describe the same physics using different basic objects. A particle in one theory may correspond to an extended object or collective state in another. If both descriptions are complete, the fundamental reality may not be identical to the apparent ingredients of either description. It may be the common structure connecting them. This creates a humbling limit on ordinary intuition. Human beings evolved to handle medium-sized objects moving at low speeds. We are good at finding food, avoiding obstacles, and noticing when somebody has taken the better chair. We did not evolve to visualize quantum fields, higher dimensional geometry, or networks without space. It is not surprising that the deepest physical descriptions resist simple pictures. A theory does not need to be visually comfortable to be correct. It must be mathematically consistent and experimentally successful. At the same time, mathematics alone is not enough. Many structures can be internally consistent. Physics must connect them to measurements. The final answer about particles will therefore come from both theory and evidence. Theories suggest where to look. Experiments determine which possibilities survive. For now, several statements are well supported. Particles do not behave like tiny classical balls. Quantum field theory describes them as excitations of fields. Identical particles of the same type are fundamentally indistinguishable. Particle number can change through interactions. Creation and destruction are changes in quantum fields rather than the unexplained arrival or erasure of substance. Other statements remain open. We do not know whether quantum fields are fundamental. We do not know whether strings exist. We do not know whether space emerges from entanglement in our universe. We do not know whether all particles are different states of one underlying system. The absence of an answer does not make the question empty. It identifies a clear research problem. Physicists can compare theories, calculate consequences, and design tests. The search may reveal a new layer of components. It may show that components are not the right idea. It may replace particles and fields with relationships, symmetries, or information. Whichever answer succeeds must explain why the particle picture works so well. It must explain why detectors record distinct events, why electrons are identical, why conservation laws hold, and why stable matter exists. It must recover the standard model where the standard model has been tested. A deeper theory cannot simply announce that familiar particles are illusions and ignore their measured behaviour. Emergence is successful only when it produces the observed level with all its regularity. A wave emerges from water, but the properties of the water explain how the wave moves. Temperature emerges from molecular motion, and statistical mechanics explains why temperature follows reliable laws. If particles emerge, the deeper theory must show why their masses, charges, spins, and interactions take the forms we measure. Until that happens, quantum fields remain the most reliable foundation for particle physics. They may not be the final foundation, but they're not a casual guess. Their predictions have survived demanding experimental tests. The responsible position is therefore neither complete certainty nor careless speculation. We can say that particles are not fundamental objects in the classical sense. In modern theory, they are excitations of quantum fields. We can also say that the status of those fields remains unresolved. This leaves us with a universe that is less like a pile of tiny stones and more like a system capable of stable activity. Matter consists of patterns that persist because the laws and symmetries support them. Your body is one arrangement of those patterns. The air in the room is another. Light reaching your eyes is an excitation of a field. The solid surface beneath you is maintained by electromagnetic interactions and the quantum behaviour of indistinguishable electrons. None of it requires microscopic hardness at the bottom. The deepest level, if there is one, may not look like matter, motion, or space. Those concepts may appear only after the underlying system is organised in a particular way. That can sound unsettling, but it does not change the reliability of ordinary life. The room remains where it was. The floor continues to resist your feet. The clock continues to move forward at the rate allowed by its location and motion. A deeper description changes our understanding, not the stability of the patterns around us. The most useful conclusion is not that particles are unreal. It is that reality may support several valid levels of description. A particle is real as a detectable excitation. A field is real as the system whose state produces that excitation. A deeper network or information structure may also be real if future evidence supports it. Each level answers a different question. When we ask what entered a detector, particle language is effective. When we ask how identical particles can exist, field language is stronger. When we ask why those fields and symmetries exist, current physics reaches an open boundary. That boundary is where strings, quantum geometry, information, and other proposals begin. They are attempts to continue the explanation, not established facts placed beneath the standard model. Perhaps future experiments will reveal that particles contain smaller components. Perhaps a new observation will support extended strings or extra dimensions. Perhaps the structure of black holes will show that space and matter emerge from entanglement. It is also possible that the correct theory will use ideas no one has yet named. Science has often advanced by discovering that a familiar question was based on the wrong picture. Asking what carries light through space once encouraged the search for a mechanical medium. Relativity showed that the assumption was unnecessary. Asking what material sits inside a fundamental particle may lead to a similar correction. There may be no inner material. The particle may be a state, a relation, or a permitted pattern. For the moment, we can return to the simple image that began this discussion. A wave appears on water. It travels, carries energy, interacts, and disappears. The wave is real, but it is not a separate substance from the water. A particle may be like that in one important sense. It may be a distinct and measurable event in a deeper system. The electron is not a tiny drop from the electron field. It is the field active in the electron way. If the field itself emerges from something deeper, the pattern continues. Fields may be the visible activity of quantum information, strings, networks, or another structure. What we call matter would then be several levels removed from the final description, yet fully real at each level where it has stable effects. That is where the evidence currently leaves us. Particles are among the most precise concepts in science, but they may not be the last word. They may be the forms reality takes when its deeper structure becomes active in ways our instruments can detect. Here in the ordinary world, that deeper activity has produced atoms, stars, planets, living cells, electrical circuits, and a quiet room in which someone can listen to a discussion about whether anything is truly made from particles. If this journey through fields, strings, symmetry, and information has given you something useful to think about, you can like the video and subscribe to Physics with William. It helps this slow approach to science reach other listeners who may enjoy learning about the universe without requiring the universe to speak quite so loudly. Wherever you are listening from, everything around you is built from structures that physics understands with great accuracy and does not yet understand completely. The particles inside ordinary matter may be temporary excitations. The fields beneath them may be emergent. The deeper foundation remains unknown. What we do know is that patterns can be real, stable, and important without being fundamental. Particles may be exactly that. They are not necessarily the permanent substance of the universe. They may be the recognizable forms produced by something deeper, following rules that allow those forms to appear, interact, and sometimes disappear. For now, the best answer is not a final object hidden beneath every other object. It is an open scientific question, supported by several serious possibilities. Reality may not be built from particles in the way a wall is built from bricks. It may produce particles in the way a field produces an excitation, a material produces a wave, or a network produces a stable pattern. The building blocks may not be blocks at all.